Hi, very good morning to all.
Good morning.
Good morning.
Good morning, sir.
Good morning, sir.
I think only 18 participants are here. We will wait for 2 more minutes.
Yes, sir. So, students, just to announce, this week's in class will contain both logistic and decision tree if it gets over, isn't it, sir? Today.
Yes, Lena, today we will be starting
If,
decision tree. So I think they can do the in class with respect to whatever that we are doing in today's session.
sure, sir, sure.
Fine, I think we can start now. So in our yesterday's session, we have discussed about logistic regression as a classification model. So we have discussed the mathematical part of the logistic regression in detail, how the concept of linear regression extended to do the classification task. So in that process, we have discussed how the continuous output of linear regression has been converted into a probability range for probability value, which means anything from minus infinity to plus infinity, how we are converting that to a range of 0 to 1. For that, we have actually used two transformations. One is exponential transformation. By performing exponential operation on any continuous output, all the negative values will go off, only the positive values will remain. Then on top of that exponential transformation, we have applied division transformation, divide by some max value. Here the max value that we have considered is 1 plus exponential of that same y rate. So after taking the exponential of y rate and dividing that by 1 plus exponential of y rate, we transformed the continuous output to a probability value between 0 to 1. So that probability value that we got, we have to infer like that is the chance that that particular observation belongs to class 1. So once we arrived at the probability value, obviously the classification result is possible. That is, even though initially we have a continuous salary value as an output, after performing this math, whenever the probability value is greater than 0.5, the machine will allot high salary class to that observation. whenever the salary value is less than, or whenever the probability of that salary target is less than 0.5, machine will allot low salary class to that particular observation. So classification task is done by just applying by just applying these two transformation and finding the probability. But logistic regression is not about just to do some kind of prediction. It is also to infer the model. It is also to make our model more explainable. So in that context, we have also tried to bring the linear relationship between the input and output. With respect to the probability value, there is no clear linear relationship because we know that the formula for probability P is exponential of y reg divided by 1 plus exponential of y reg, or exponential of z divided by 1 plus exponential of z, where z is the linear regression of equation. So if you see that equation is a nonlinear equation. So obviously we can't explain the impact of input on the output linearly. In order to bring that sense, we have just expressed P in terms of odd ratio. So we have computed P divided by 1 minus P. So we know the expression for P by subtracting 1 from it and again dividing it, lead to a value e to the power of z. So odd ratio P divided by 1 minus P, we ended up with the expression e to the power of z. But still there is an exponential term which lead to a kind of nonlinearity. So what we did, we have taken that exponential on the other side. So P divided by 1 minus P, now it becomes ln of P divided by 1 minus P, that we used to call it as logit ratio. So now that logit ratio, which is equal to just z, the expression just becomes like logit ratio is equal to z. So which means z is nothing but your linear regression output, which is nothing but b1 x1 plus b0. So now the relationship between x1 and logit ratio or logit are very linear. So we can explain what is the change in the x1 will affect or will change the logit. So that is the kind of extra transformation we did in terms of odd ratio and in terms of logit, so that we make our model more explainable. That is the reason why logistic regression is also known as linear model, right? So this is what the things that we have discussed in our last session. Today, our agenda will be how to evaluate the performance metrics of classification algorithm in general, not just only with respect to the logistic regression. All the metrics that we are going to discuss in today's session, it's common for all the classification algorithm, right? So we are going to spend the first half on understanding the different measures. It's not just two measures as we used to discuss in linear regression, only R square and MSE, that is RMSE or MSE, that error measures are there in a linear regression. Here we are going to discuss so many measures, and we are going to discuss in detail what is the advantage of one measure over the other, in which situation I will define my model performance with this measure, at which situation I should not define my model performance with this measure. All those things we are going to discuss in detail, which is very important in model building. And the later part of today's session, we are going to jump into decision tree. So which is the second machine learning classification algorithm that we are going to discuss today. So that is the agenda for today's session: metrics and decision tree. So I hope that everyone have that Jupyter notebook that we have used in our yesterday's session. Let me share my screen. Fine. So let me quickly list the different performance metrics. Then one by one we will go into it. So the first famous metric is accuracy. Accuracy score. right? So then we are going to compute something called recall, precision, F1 score, specificity, ROC, AUC. So these are all the kind of standard measures through which, or standard metrics through which we are going to evaluate the quality of our classification model. So for finding all those measures, whatever the measure this is, whether it is accuracy score, recall, precision, F1 score, specificity, or even some other measures like sensitivity, false positive rate, right? So whatever it could be, we need 4 measures or 4 values to compute all those things. That 4 measures are TP, TN, FP, F1. If you go and see the mathematical formula for any of those measures, all those measures mathematical formula is consist of only these 4 terms: TP, TN, FP, F1, directly or indirectly. All those measures has been expressed with these 4 measures. So it is very important to understand these 4 measures in detail. It is very important to compute these 4 measures from our model, so that once we compute these 4 measures, then getting all those measures is simply applying in some formula. And also in sklearn, even we don't need to apply in that formula. By just calling its corresponding function, we can get everything. But understanding all those measures is very important, because at the end of the day, I want to define my model in terms of what measure is key, right, with respect to the business aspect, whether I have to give the importance to accuracy score, whether I have to give importance to recall, whether I have to give importance to precision. That is very, very important, right? So it is not like you can just define your model with any of this measure. So each and every measure is have some kind of merit over the other, and the same time each and every measure is also having some kind of demerit over the other. So we are going to decode that in detail in today's session. So before going into that measure, we have to understand what is TP, what is TN, and what is FP, and what is F1. Let me explain that with one example. Say I have some actual data. Say my task is to predict cancer, right? So the first observation in my only the target column that I'm writing, I'm predicting the cancer based upon so many input features like tumor diameter, tumor volume, tumor coarseness, tumor smoothness. So I just scanned the tumor. From the tumor image, people did some kind of image processing stuff, or they have done some kind of bioscopic test, and they have come up with different measurements of the tumor and different texture features of the tumor. Based upon the texture features or shape features of the tumor, my job is to predict the malignancy nature of the tumor. So the actual data, of course, with supervised algorithm, I always have the actual data. So that is the past label data. The past label data is saying that the first observation is on cancerous patient. The second one is non-cancerous. The third one is also non-cancerous. The fourth one is cancerous. And the fifth one is non-cancerous, then cancerous, then non-cancerous, then non-cancerous. Right? So this is the real data. Say this is the hospital record, right? Doctors already diagnosed through their expertise, and they have marked this person is having cancer, this person is not having cancer, something like that. Now I am building the machine learning model to predict the same, right? So my predicted output, this is actual output data or output. Now my predicted output is, the first one is cancer, the second one is also cancer, third one is no cancer, the fourth one is no cancer, the fifth one is no cancer, here it is cancer, here it is cancer, here it is no cancer. So just to properly differentiate, I'm just putting a line to avoid confusion. right? So this is the actual output and this is the output predicted by my model. Say I have built the logistic regression for this and logistic regression is giving this output to me. Now, what is true positive? So with respect to this table, I'm just going to compute these 4 measures. So everyone now have this ability to compute this predicted output, right? At the end of last session, after finishing our last session, everyone have this ability to apply your data in logistic regression model and get this one column, right? Yes or no?
Yes, sir.
But anyway, it won't be NC, it will be cancer, we will represent with 1 and the non-cancer we will represent as 0, right? But anyway, we can predict this one column of output for any given input. So now, with respect to this, how can I find TP? How can I find TP? TP is true positive. True positive, which means, first of all, for any work, you have to identify which one is positive, which one is negative. Machine don't have that kind of understanding, right? So machine just like that will tell one case is positive, one case is negative. But it is up to you to consider which one you are going to consider as a positive and which one you are going to consider as a negative. In this case, we have 2 class, cancer and non-cancer. Which one you want to consider as a positive and which one you will consider as a negative?
When we value same, then we can say true positive.
When predicted and actual are same.
No. Forget about true positive. I will come to it. So generally there are 2 class. One is cancer and another one is non-cancer. I'm just asking between these 2 class, which class you will consider as a positive class, which class you will consider as the negative class.
Cancer
Cancer is positive.
Right. So we will generally in medical world, if a disease has been diagnosed, we will consider that as positive. So cancer is positive case and non-cancer is the negative case. So now with respect to this, true positive is nothing but how many cases correctly identified as positive. How many cases correctly identified as positive? What is positive? Cancer. So how many cases are correctly identified as cancer? Which means actually he is having cancer and my model is also predicting that he is having cancer. Right? So really the patient is having cancer and also my model is correctly predicting that he is having cancer. So that is actually true positive. So with respect to this, how many cases are true positive?
2.
So this one and this one, right?
Yeah.
So true positive is 2, right? Now come to true negative. True negative TN, true negative is the same inference. How many negative cases are correctly identified as negative? How many non-cancer cases are correctly identified as non-cancer? So in both the column, in how many places NC is there? Actually, that person is not having cancer. My model is also saying that he is not having cancer. So how many cases are like that?
3.
3.
This is one case. This is the another case. And this last one is another case. So TN is 3. Now, the next measure is false positive. Use some other color. False positive, FP. So false positive is my model wrongly branded them or wrongly classified them as positive. Actually, they are negative. Actually, they don't have cancer, but my model is telling that they are having cancer. My model is predicting them as cancerous patient, but they are not actually cancerous patient. So in actual data, it must be NC, but the predicted column, it must be C. So in how many cases that was the situation?
2.
2.
So falsely, it has been predicted as cancer. Actually, that patient is the non-cancerous patient, but my model is predicted him as a cancer patient. So NC and C. So in 1, 2 cases. So FP is 2. What is FN then?
False negative.
Negative.
Which means falsely my model is telling that they are not having cancer. My model is predicting that they are not having cancer, but it is false. Actually they are having cancer. But my model is predicted them as non-cancerous patient. So how many cases are like that? How many cases are like that?
One.
Only one.
One case.
So here only one. So actually they are having cancer, but my model is predicting that they are not having cancer. So false negative value is 1, right? So once we computed these 4 things, we can easily compute all other measures, right? So now before going into those measures, say with respect to this cancer prediction case, for which one you will give more importance? So which one you are calling, which one is good, which out of 4 measures, which measures are good measures and which measures are error measures? Out of these 4 values, TP, TN, FP, FN, which are all the correct prediction and which are all the wrong predictions?
TP, TN is
TP,
correct prediction,
TN.
and then FP, FN is a wrong prediction.
So TP, TN is the correct prediction, but TP is the correct prediction with respect to positive, TN is the correct prediction with respect to negative, and both FP as well as FN are wrong predictions. So obviously in any model, we want both FP and FN to be low, and we want the TP and TN to be high, but still always we can't just like that achieve, right? So in some kind of situation we will be in the position to I'm kind of fine if false positive is kind of high, but I don't want any false negative to be happen in my model. In some scenario I'm fine with false negative, but I don't want any false positive to be happen in my model. So it's a kind of trade-off, right? So ideally speaking, I want both false positive and false negative to be low, but it is not possible in all those cases. And in some domain, I'm fine with sacrificing one over the other, or I'm just bringing some kind of trade-off. I'm just okay with having a little bit high false positive at the cost of having, with the benefit of having very low false negative. So with respect to this cancer domain, for which one you think you want to reduce between false positive and false negative?
False negative should
False
be
negative.
False negative should be low.
reduced
Why?
because the actual also wrong and the prediction entirely goes wrong.
No,
Okay.
it's more risky if we don't treat.
Yeah, that
We
is
don't
what
treat
I
the
mean to
person.
say.
Exactly. So it's more risky if you don't treat the person. So just replace the cancer with COVID. So say this is the COVID output, right? Whether they are having COVID or not having COVID. So if I wrongly say like somebody is not having COVID, but they are actually really having COVID, they will go out and spread that disease to many people, right? Exponentially. So in that case, I have to be very careful with the false negative. I have to make sure that my model should not give any false negative. So at the cost of even declaring some non-COVID patient as you are having COVID, right? So they may isolate themselves for a few days, and after doing the test once again, they may free to go out. But at the same time, if I wrongly say some COVID patient like you don't have COVID, and if he goes out and spread the disease, so it is a kind of dangerous situation than me. So it is dangerous situation in this case. So in this COVID case or in this cancerous case, we will be giving more importance to false negative compared to false positive, right? But at the same time, we can't compromise more on it. So if we keep on increasing false positive, many patient will get panic, right? So somebody may hang himself, but if we say wrongly that they have cancer. So that also we have to avoid. But the thing is, which one I have to give more priority. So in some situation, I will be in the position to give more priority to false negative over false positive. In some situation, I will be in the situation to give more priority to false positive than false negative. Can you give me any one example? I have given this COVID example and cancer example where we have to give more importance to the false negative than the false positive. Can you give me any other example where you need to give more importance to false positive than false negative? That is, I'm fine with even if there is any false negative, but I'm very much careful on false positive. I don't want any false positive to be in my model.
Uh,
Sir,
maintenance of industry like pipelines or industry things, preventive maintenance kind of situation.
Can you give a little bit more explanation on it? Why false positive is very much critical in that case?
Because I mean, if the production stops, the cost is too much. So even with few false negatives, having preventive maintenance is fine. So having a false positive would impact more.
Yeah. So sometime in the atomic power station and big power station, because of false negatives or because of false positives, if you just halted the whole power station, what happened? Then again starting that whole power station and start to produce that electricity or start to produce the output once again may take even 3 hours, 4 hours, 5 hours, right? Just by trusting the false positive, if you just halted the whole system, again to restart that system, it may take even hours, right? So which will ultimately affect your business, right? That is one part. One another easy and classic example that I can give, like spam and not spam. So in our Gmail, some Gmail is automatically applying some kind of text analytics based classification algorithm, and they are sending some messages to our primary inbox. Some messages automatically they are just pushing that to spam, right? So what happened in this case if false positive is high? In this case, if false positive is high, what will happen?
important mails are missed.
Important mails missed means important mails, say in this case, spam is positive. In this case, I told spam is positive and non-spam is negative. Then false positive means some non-spam message. False positive means some non-spam message go into spam, right? So actually that message is not spam, but as false positive is high of your for your model is actually categorizing that particular mail as positive, as spam, and it is pushing that into your spam folder. We don't have this habit of checking the spam folder often. So say that is your interview call letter and you have to report to them within 1 week, otherwise that offer is not valid. Then obviously you are seeing that spam folder after 10 days, obviously you will lose that job, right? So that is more serious, right? So in that case, so in these kind of scenarios, one another example that we just discussed, the manufacturing unit or this spam, non-spam example. So these are all the kind of model for which we have to give the more importance to the false positive. The focus will be on reducing the false positive. So even if false negative is slightly high, I'm fine with it. What going to be happen? Some spam message is going to come to my primary inbox. But after seeing that, I can understood that, and I will even Gmail is providing the option to push that to spam so that they can learn something from our activity. So kind of reinforcement learning. But anyway, so coming some spam message coming into my inbox, it's not really affecting me unless otherwise I click some kind of unwanted link within that mail. Otherwise, I can simply delete it or push it to spam. That's fine. But if my important message goes into spam, and if I missed that message completely, then obviously that loss will be more. So in that case, so domain to domain, you should have some kind of domain sense to understand whether I have to give the more importance to false positive or false negative. But ideally speaking, I want both the things to be as low as possible. Everyone clear with this? TPT and FPFN?
Yes, sir.
Right? Fine. So now with the help of these 4 measures only, we are going to define we are going to define all other things. Let me save this.
Sir, one question.
Yes.
Cancer taken as positive and non-cancer taken as negative, that is the standard format we follow, sir.
No.
Can
Actually,
that go vice versa?
no. So the thing is, automatically based upon the occurrence of the level in this data, the confusion matrix has been framed, right? So we have to count it, how many positive cases are there, how many negative cases are there in our data. And with respect to that, once this 4 value printed by your sklearn, we have to understand which one sklearn has been considered as positive, which one sklearn considered as negative. So there is some kind of randomness. It is based upon the label of that particular output column. In alphabetical way, it is actually considering the first one as positive, second one as negative, something like that it is doing. So we don't worry about it. I'm just going to tell you how to, once your sklearn matrix is giving you the TP, TN, FP, FN, that is 4 numbers it will give. It won't tell that it is TP, it is TN, it is FP, it is FN. So it just give 4 numbers to you in matrix form. It is our responsibility to notate which number to false positive, which number to false negative, which number to true negative, and which number to true positive. Got the point?
Got it, sir.
Right? So just we are going to do that in Jupyter Notebook. But Jupyter sklearn packages or Python program don't actually have the ability to say this is positive, this is negative. It just give 4 numbers. Whenever this and this match, whenever this and this these 2 columns are matches, how many class 1, how many is there, class 2, how many is there, class 1, class 2, how many is there, class 2, class 1, how many is there, like that only it will give. So it's our responsibility to name it as TP, TN, FP, FN. That we are going to do in a moment now. So now let me take you to these 4 measures or 5 measures before implementing this in Python. The first measure is accuracy. So I think you can easily tell the accuracy formula with respect to these 4 measures. Can anyone tell? So it is like how many correct prediction out of total observations. Accuracy is a kind of measure how many correct prediction out of total observation. I'm asking you 100 question and you are answering it correctly. It is 80 by 100. That is your accuracy. Yeah.
5 by 8.
TP plus TN.
TP plus TN.
TN by
TN total.
plus TN plus FP plus F.
Exactly. Right. So if you add all those 4 numbers, TP, TN, FP, FN, which is nothing but total number of observations in your data. So out of the total number of observations, how many are correct predictions? You people only told that true positive and true negative are correct predictions and false positive and false negative are wrong predictions. So TP plus TN divided by TP plus TN plus FP plus FN will actually gives you the accuracy of your model. Now, let me give one example. There are 100 patients. Out of 100 patients, 95 are not having cancer and 5 are having cancer. Right? So this is the original data. This is the data set information. Actual. Right? So I built the model to predict it. My model predicted this as so 3 cases are fine. So 2 cases it is predicted as cancer. Right? So out of 5, out of this actual 5 cancerous cases, only 2 cases it has been predicted as cancer, and remaining 97 cases is predicted as non-cancer. It's predicted as non-cancer. Can anyone tell what is the accuracy score for this?
99.
90?
99.
99. Any other answers? let me draw the confusion matrix. So there is some standard way to put the confusion matrix, and also in R and in Python, the structure of the confusion matrix is little bit different. So if you see in which place I have to put FP, which place I have to put FN. So don't freeze the boxes. Don't freeze the boxes, because that depends on which side you are giving for prediction and which side you are giving for actual, and which row you are giving for positive and which row you are giving for negative case. Say the first row I'm just allotting for positive case, and second row I'm just allotting for negative case. So here also first column I'm just allotting for positive case, and this second column I'm just allotting for negative case. And this side is actual side, actual output, and this side is for predicted. This side is for predicted. So actual, this side is actual side and this side is the predicted side. And first row, I'm just going to capture all the positive information, and the second row, I'm going to capture all the negative information. So say this is the structure. Now, here, with respect to this kind of two cases that I have told, so here first, just write which one is true positive, which box is here true positive.
Cancer.
First
Sure,
First
and
one.
this is true positive, and you are, so this is true negative.
True negative.
Actual also negative, predicted also negative, so it is true negative. Here actual also positive, predicted also positive, so it is true positive. Which one is false positive?
So second one. That one.
Yes.
No,
Right.
no.
Hmm.
The opposite one.
What is the meaning of this box?
Actual is negative, but the predictor is positive.
So it is a false prediction, right?
Positive.
Yeah, false positive.
Yeah.
This is false positive, right? Is everyone agreeing this? This is false positive, because actually it is negative, but my model is predicted as positive. Falsely, my model predicted as positive,
False positive.
right? So this one is so false negative, but don't fix the places. Don't fix in your mind like always this box is false positive, always this box is false negative. It is based upon the way that we are actually considering the which one is the predicted side and which one is the actual side. The same confusion matrix I can also write by putting actual here and predicted here. Then the analogies will vary, right? Similarly, I can use the first row for negative and second row for positive in the sense. Again, the analogy will vary, right? Yes or no? Are you getting my point?
Yes, sir.
Right.
Yes,
So
sir.
in that sense, so just when whatever the way that you are actually constructing this confusion matrix, with respect to that, you have to mark which box is true positive, true negative, false positive, and false negative. Now, with respect to this example, can you tell me the count? What is the value that I have to put it in each and every box?
True positive 95.
TP is 2.
Which one is positive here, cancer or non-cancer?
Cancer.
Generally, we are going to consider cancer as positive, right?
So the first
but
one
sir,
will
here-
be
So this is the aggregated numbers. Right now we don't have a TP or FN defined, right? Here?
Here in bracket, I have written out of 5, right?
Okay, okay. Yeah.
so 2 will be the first one.
So that is the reason specifically I have written this 2 cancer. Out of this 5, it is actually identifying as 2. So which means true positive is only 2, right?
2, correct.
Yes.
Yeah.
Yeah.
True
Right?
negative
Total is only
97.
99.
Sorry.
Total is only 99 results.
Sorry. Here 2, so 3 will come here. So it is 98. This one is 98. Right?
Yes,
Now what about the true negative?
Sir, what do you mean by out of 5?
Out of 5 means this is actually I have my data set. In that there are totally 100 patients are there.
Yeah.
Out of 100 patients, 95 patients are not having cancer and 5 patients are having cancer. This I know. By seeing the data itself, I know, because this is the past data. This is a label data that I have in my hand. Now I'm just building my machine learning model. My machine learning model is predicting this. It's predicting only 2 cancerous cases, 2 patients as cancerous out of that 5. I know in my original data there are 5 cancerous cases, no? So out of that 5 cases, it is actually predicting only 2 is having cancer.
Yeah, so while predicting, we
So the
already
remaining
know
3,
that it's all 5.
the remaining 3, it is actually pushing to, it's actually considering predicting as non-cancer.
False
So
positive.
95 non-cancer plus 3, totally 98 cases, it is actually considering as a non-cancer. It is same as that of the previous one. Previously only 5 or 6 observations, so I have shown in 2 columns. Now for 100 observation, I can't write it.
Yeah.
That's the reason why I have given like this. Right? So now can anyone tell how many true negative?
95.
Right, because if you see in total there are totally actually there are 95 non-cancerous cases. Truly there are 95 non-cancerous cases, but my model is predicting 98 non-cancerous cases, but out of that 3 cases it is wrongly predicting. So the true negative actually 95. My model is also predicting the same all the 95 cases correctly as non-cancerous. So true negative is 95 here. What about false positive? What about false positive?
I think it's 0.
Nothing. Zero.
False positive is any
0.
non-cancerous cases your model is predicting as cancerous? No, right?
No.
No. So your false positive here in this case is 0. What about false negative?
3.
Negative means it is actually cancerous, but my model is wrongly predicting that as non-cancerous. Out of those 5 cancerous cases, only 2 it is actually predicting as cancer. The remaining 3 it is actually predicting as non-cancerous. So falsely it is predicting as non-cancerous case. Non-cancerous is the negative case for us. So F1 is 3. Please let me know if you have any doubt. Of course, if you have 2 columns, then by simply comparing how many CC is there, how many NC is there, how many CNC is there, you can easily write it. But the same thing only here also I have done. But as I consider some big data, I have not actually displayed as 2 columns. I have just written that in an abstract level. With respect to that, I have framed this confusion matrix. Everyone understood this? How these numbers are coming inside this confusion matrix?
Yes, sir. Sir, wouldn't it be easier to say that the actuals, we know the totals, we can put the totals at the end, and then the true positives and true negatives we know, and then we take the difference to fill up false negatives and false positives.
Yeah, of course. Anyway, in say any kind of shortcut you can follow, and also we are not going to do this process with pen and paper while you are building our algorithm, right? So anyway, it's, that function is going to give that values. So just to understand it, we are doing like this.
Sir, I have a question. In previous example, there we discussed, right? So here we are assuming that for cancer, we are assuming it is true positive, and non-cancer patient, we are assuming true negative, right? So
No. See, cancerous patient, we are assuming as positive, not true positive.
No, so it depends, right? I mean, based on the count.
Yeah, say here cancer. Say for this, say I'm just writing this with an ratio of 1095 means say if I'm writing the same thing with 2 columns, you can easily understand, right? So this is actual, and this is predicted. Say something is there as cancer, non-cancer, cancer, non-cancer. You can easily understand this, right? As we did previously.
Yes, sir.
So the same thing only here also I have written. The only thing is I have written in an abstract level, like for that 100 observation, I have to write something like this, and then I have to tell. So now I have just written this in an abstract level, and I'm always in healthcare domain. Whenever the disease is there, we will consider that the disease case is a positive case. The non-disease case we will consider as the negative case. So here cancerous case I'm just going to consider as positive. Non-cancerous case I'm going to consider as negative. Now my question is, I have to find true positive. True positive means how many cancerous cases correctly identified as cancerous by my model. With respect to this number, can you tell that? How many cancerous cases correctly identified as cancerous by my model?
2.
2. So that is the reason why I have written true positive as 2.
No, so sir, my question was related to which one we should consider for positive and which one we should consider for negative. Okay, like
No, say the same thing I can also tell by considering cancerous cases as non-cancerous cases as positive and cancerous cases as negative. Also, I can frame and I can define my answer. I can form all those. I can compute all those outputs, accuracy, everything with respect to non-cancerous case. If I consider positive case as cancer, that accuracy I can relate like accuracy is 80% means I have to understand that 80% as it is the ability of detecting the cancer. Or say I'm computing the recall. So that recall I can understand like this is the ability, my model ability to understand the cancer is this much percentage. If you consider your true positive as non-cancer, then that recall value you have to understand like my model ability to understand the non-cancer is this much percentage. So if you are defining your true positive, if you are defining your positive with cancer, then whatever the measures that you are calculating, you have to speak with respect to cancer. If you are defining your positive case with non-cancer, whatever the measures or whatever that metrics that you are computing, that you have to speak in terms of non-cancer.
okay, so that we need to decide right before computing all this thing.
Yes, so generally in healthcare domain, so I will speak everything in terms of how many people are got the cancer, how many people diagnosed with the COVID. So like that, I will speak. My focus will be on identifying the cancerous case. My focus will be on identifying the COVID case. In that case, I will consider that as positive.
Correct. Yeah.
So you say you are actually doing some kind of attrition ratio. So attrition prediction. So like churn prediction, how many people will stay with me and how many people will leave. So in that case, say in your data set churned people you can consider as positive, or churned people you can also consider as negative. So it is based upon your sense only. You have to have some kind of proper understanding over, say if you consider some level as positive, whatever the results that you are telling, it's actually telling with respect to that positive case. Whether which one has been taken as positive or negative, it's purely up to you.
Yeah, okay. Yeah.
Yeah. So now after getting this numbers in this boxes, can you tell what is accuracy? By substituting in this formula, what is accuracy?
97 divided by 100.
97 divided by
100.
100, right? So it is 95 plus 2 plus 0 plus 3. So it is 97%. So my model accuracy is 97%. Do you really think this is a good model?
No,
No, sir.
Why?
this is biased.
No. The bias, all those things we will come. But generally, what do you mean by bias?
Have more false negatives.
More false negative when compared to.
If we just say that everything is non-cancerous, even then I think we'll have 90%.
Exactly. Say here, my main objective of building this model is identifying to identify the cancer patient. But my model is not actually doing well in terms of identifying the cancer patient. Out of 5 cancer patients, my model is actually predicting only 2 patients correctly as having cancer, right? But still I'm getting the accuracy because my model have the ability to identify the non-cancerous cases correctly as non-cancerous. In terms of identifying one class, or in terms of predicting one class, my model is doing well. Whereas in terms of predicting the other class, my model is not doing that much well. Are you getting my point? Yes or no? This model is doing well, really well, in terms of predicting non-cancerous patient as non-cancerous. Whereas this model is not doing well in predicting the cancerous patient as cancerous. Is everyone agreeing that? Right? So that is the reason accuracy is not the measure that you can always trust. Why this problem is coming? Because this data is imbalanced. The data is imbalanced. Whenever we have an imbalanced data, accuracy score is not a good measure to evaluate its performance. Accuracy measure is not a good measure to evaluate its performance. Why I'm saying this data is imbalanced? What actually makes me to tell that statement?
Because the ratio of the cancer and non-cancer is
Ratio of the cancer and non-cancer. Out of this 100 patient, the ratio is 95 is to 5. Right? Right? So this is only 5% of data is representing one class, and the remaining 95% of data is representing some other class. Right? So obviously this is imbalanced data. So in our coming sessions, we are going to discuss some techniques how to make our data balance and all those things. But as of now, you just understand whenever your data is imbalanced, obviously you should not go with accuracy metric. So we have to see, or we have to explore some other metric to overcome this problem that we are witnessing here with respect to accuracy. If your data is balanced, then fine, you can go with accuracy. But if your data is not balanced, then obviously you have to think of other metrics.
But sir, from business perspective, I mean, there will always be case of this only, no? Like out of 100, 5 will be cancerous and 95 will be non-cancerous.
In many domains, the data is imbalanced. So like this healthcare, you can't expect everyone to have cancer, right? Then fraud detection, credit card fraud. So obviously all the transactions are normal transactions. Very rarely only some transaction going to be in fraud transactions, right? So even defaulters, loan defaulters, most of the people will pay their loan properly. Only some section of the people may not pay back their loan. So most of the domain cases are kind of imbalanced data. So in our coming session, we are going to discuss some algorithm like random forest and all those things. Those algorithms by its math itself have some ability to handle this imbalanceness. But anyway, still if it is required, there are different techniques like upsampling, downsampling. So one way is increasing the minority sample count synthetically, and reducing the majority sample count synthetically may bring kind of balance, so that my machine learning models can learn something from both the class. It is about not making the data perfectly balanced. I don't want like class 1 should be 50%, class 2 should be 50%. Need not to be. I have to increase the balanceness such that I have to bring out the balanceness such that my math of my machine learning model is understanding something from both the class. Both the class characteristics it need to understand. For that, I need to provide enough amount of data, right? If I'm not at all providing the data, how can I expect my machine learning model to understand the data characteristics? So only 5 observation I'm just giving for cancer, 95 observation I'm just giving for non-cancer. With that 5 observation itself, my model need to understand the characteristics of the cancer patient or cancer tumor. In the sense, sometimes model may not understood that with lesser amount of data. For machine learning model, data is the fuel. More the data that we will give, my model will understand the characteristics of the data well. So obviously in that point, we have to increase the count of minority class, but it need not to be exactly equal to the majority class. Say from 95 to 5, even if I'm increasing to 20%, 5% of data, I'm just synthetically increasing to 20%. If my model is good enough, or my model math is good enough to understand the characteristics of my cancerous data or cancerous patient with the help of that 20 observation or 20% of observation, then it is well and good. I can stop at that point of time itself, right? So like that, some kind of strategy that we are going to discuss. But as you told, in many domain, the data is kind of imbalanced one. So obviously, we have to make that as balance, or some other machine learning algorithm that we are going to use in our coming session by default can handle this, right? So now, say the conclusion is like for imbalanced data, we should not go with accuracy score. Now, then what I can do? How can I measure the performance of the imbalanced data then? How can I understand? Say, if it is an imbalanced data and if I go with accuracy, 97% accuracy, I should not feel happy for that, right? I have to see the other other metrics also. The other metric is recall. The other metric is recall. For recall, the formula is TP divided by TP plus Fn. TP divided by TP plus Fn. Oh, I have written that in the previous. Okay. Can anyone? So let me just. Previously, this box we consider as TP, TN, FP, Fn. Can anyone tell what is the value that we got here? 2, right? 2, 95, 0,
3.
3. So this is your predicted side. This is your actual side. This is actually cancer. This is non-cancer. This is cancer, and this is non-cancer. Now, if you closely look at this formula of recall, so TP plus Fn, TP plus Fn is the sum of this first row, right? The denominator, this part.
Yeah.
Right. So, if you see, this is for actual cancer. This row is for actual cancer. If you sum it up all those element here, you will get 5. What is 5? 5 is nothing but total number of cancer patient in my actual data, in my original data. So recall is a kind of measure which will finding how many patients are correctly diagnosed as cancer out of total cancer. Right? So how many cancer cases are correctly identified out of total cancer cases? So recall is simply how many cancerous cases or how many positive cases are correctly identified as positive out of total positive cases. It is not actually seeing with respect to the whole data. It is actually seeing with respect to one class only. So out of the cancerous class or out of the cancerous data, how many cases are correctly identified as cancerous? So if you substitute in this formula, what is the TP? TP is 2. 2 divided by 2 plus 3. So which means out of 5 cases in this data, totally only 5 cancerous patients are there. Out of the 5 cancerous patient, how many patients are correctly identified as cancerous patient by my model? That is what recall is all about. So if you compute this, what is this value? Can anyone tell? 2 divided by 5, how much?
40%.
40%.
Right. So now we are getting some more quality about my machine learning model. Even though initially in previous workout, we saw that accuracy is a 97%, we can't overwhelm with by that. We can't really feel happy for that, because by saying the recall, we come to know the recall value of my model is only 40%, which means my model ability to identify the cancerous case is only by 40%. Right? My model ability to identify the positive case, in this case cancerous case, correctly as cancerous, is only by 40%. So which means if accuracy is high but recall is low, then you have to understand that my model ability is good in understanding one class, but my model ability is bad in understanding the other class. Here in this case, my model ability is good in understanding the non-cancerous case, but my model ability is poor. My model ability is only about 50%, 40% in understanding cancerous case. So this recall measure is also known as sensitivity. It is also known as true positive rate TPR. Right? There are some other names for this recall. Recall is also known as sensitivity. How sensible my model is, how sensitive my model is in identifying the positive cases, and also it is also known as true positive rate, because it's going to do something with true positive. True positive divided by true positive plus false negative, because the false negative is also actually it is positive. False negative is something my model predicted as negative, but really it is positive. Right? So out of total positive cases, how many cases are correctly identified as positive? That actually given by my recall. Any doubt in recall? Understood the recall measure? Yes or no?
Yes, sir.
Yeah.
So what is this TPR?
True positive rate.
Okay.
Right. Then the third measure is precision. The formula for precision is TP divided by TP plus FP. So if you see TP plus FP, it is this part, right? TP plus FP is this part. So this is totally, so this denominator is actually talking about totally how many cases are predicted as positive. So here the denominator is totally how many cases are actually positive. Here the denominator is talk something about totally how many cases are predicted as positive. Right. So here in this case, say what is the problem with recall before going into the precision? Say let me give another example. The same 100 patient. Out of that 100 patients, say 95 patients are having no cancer and 5 patients are having cancer. So this is the actual original scenario about the data. I'm building the model for this. My model is telling that all are having cancer. My model is telling that all having cancer. Everyone is having cancer. That is what my model is predicting. Right? For any given input, it's predicting that output is cancer. So in this case, can anyone calculate recall?
Will be 100. 100%.
Yeah.
Everyone agreeing this? So,
Yes.
say somebody given the task of predict the cancer. I'm just telling that everyone is having cancer. So if you go and calculate recall, you will get 100% because just like that you are telling all the people are having cancer. So definitely your model, as you are telling everyone is having cancer, definitely your model will also predict that real people who are having cancer as having cancer. Right. So in that sense, recall not be helpful. Say which means so in this case, what is the nature of false positive and false negative? What is the nature of false positive?
Uh, 95.
95.
Right. So it is very high. Of course, here in this case, 95 because 95 non-cancerous cases it's telling us non-cancerous. So whenever false positive is very high, as in this case, recall is not a good measure. Because recall is not actually care about the false positive. Because in this formula, you have only false negative. So it don't care about the false positive. So if false positive is very high in your model, irrespective of having the high false positive, your recall value could have been very high, right? So that is the reason because recall is not actually sensitive to false positive, right? So it is not actually bother about the false positive. So that is the reason why we need one another measure like precision, right? So now the formula for precision is TP divided by TP plus FP. So with respect to this, what is the value? What is the answer for precision? What is the answer for precision?
5.2%.
2 divided by
2 by 2.
false positive 0 only, no, in this case.
Yeah, plus 0.
How much?
100%.
100%. Right. So say in which case I have to see the false positive. This precision is whenever I feel like my model can. So whenever you feel like your model should not have false positive, like the spam, like the spam example that I have given. For that spam example, will you go with recall as a measure or precision as a measure?
Recall.
Recall is good.
Will you really go say I have given 2 examples, right? Previously, one is cancerous of COVID The another one is spam. Between these two things, say you are building a model for predicting the spam, whether you will go with recall to evaluate your model performance or precision to evaluate your model performance.
Precision.
For spam, we can go with recall. Why? Because even though few mails are missed, it's okay. But in COVID or cancer, even if one cancerous patient is missed, it is a problem.
Yeah, then that
So
will be captured in
here
recall
we can
only,
go
no?
with precision.
That will be captured in recall only, no? If even one cancerous patient is missed, that is a problem. That is what you are telling.
Yes.
That is actually reflected in terms of false negative, right? Yes or no?
Yes.
So that is actually in terms of say one cancerous patient really is having cancer, but your model is telling that he is not having cancer, which means false negative is high, right? It is false
Yeah.
negative, right? Yes or no?
Yes, yes, it is false.
So false negative is actually in the expression of recall, right? So if you want to tackle that issue, then you have to go with recall. So for the cancerous patient kind of thing, COVID patient kind of thing, you have to go with recall. Whereas in that spam example that I have given, in the spam example, I want to control the FP. I don't want FP to be happen, false positive. Falsely, I don't want to push any mail to my spam. So I want to reduce the false positive. So in that context, I want very high precision. High precision means, what does high precision means? How can you repeat high precision and false positive? If high precision means false positive is less, right? Yes, sir.
Yes.
Right. So whenever you want false positive to be less for that kind of model, you have to give more importance to precision. Whenever you want false negative to be less in that kind of model, you have to give importance to recall. But obviously, both recall and precision to be high. In other words, both false positive and false negative should be low. That is what our main objective. But sometimes, even if we can't achieve both, which one I have to give more importance? That you have to understand from your problem domain, and based upon that, you have to tune your model. So I want high precision. So tune your model with high precision and get the hyperparameters, which will give the better performance in terms of the precision rather than the recall. Right. So this is about these three measures: accuracy score, recall, and precision. So before going the other measures, I think we can straight away study in the Jupyter notebook itself. So what we can do now is straight away we can go to
Sir,
the yeah.
one question. I mean, can you repeat that for when to give importance for recall or precision?
See, it is say whenever you want your false positive to be less for your model, like in that spam case. In that spam case, I want false positive to be less, right?
Yeah.
So if I want false positive to be less, I have to pick the formula which is in terms of false positive. Right. So out of the say whether recall is sensitive to false positive or precision is sensitive to false positive.
Precision.
So which means I don't want a false positive to be high, then I have to choose precision, right? Then only I can understand whether my false positive is high or low. If I choose recall in that case, recall is not at all sensitive to false positive. Even though your false positive is high, recall score also could have been high.
Yeah.
Are you getting my point?
Yeah, yeah.
Right. So it is based upon whether you want to give more importance to false positive or false negative. With respect to that, you have to choose recall or precision. If you don't want false positive in your model, then you have to make sure that precision of your model to be high. If you don't want false negative to be in your model, you want recall score to be high. So if I'm doing the COVID case prediction, I want my recall value to be high. If I'm doing spam prediction, then I want precision to be high.
Yes, I got it. Thank you.
Yeah. Fine. So I hope that everyone have this Jupyter notebook with you. I'm just going to continue in this. So confusion matrix, obviously, we have just printed this or I have written one column as actual and one column as predicted, and by comparing that actual column and the predicted column, I used it to compute all those false positive, true negative, false negative, and all those things. That is not possible here as we have so many number of observations. The one thing is we can put some kind of for loop and you can compare whether the first element and second elements are same or different and all those things. But anyway, no need to just do all those stuff. Simply we can use one package from sklearn. So from sklearn dot metrics. So already we have used this for our linear regression itself. R square, mean square error, all those functions we have taken from here. From the same place, there is something called confusion matrix. So one by one I will load. If I just like that load all those functions, you may wonder why I'm loading all those things straight away. So I'm just loading this one by one. So confusion matrix, for this I have to give two data. One is my actual output. My actual output is y test, that is test portion, and my predicted output. Can anyone tell in which variable we have our predicted output? Not in terms of probability, in terms of value. We have in ypred, right?
Ypred.
Right. So y test, comma ypred. So the moment that I type, I'm just getting this matrix: 34, 5, 8, 33. Right. If you want to see this in a cool way, you can use heat map. sp.heat map of this whole thing, comma not equal to true. Right. So of course color and all those things you can control later. So we are getting like 34, 8, 5, 33, and it is actually telling that it is also actually labeling that 0, 1. So in this data, between test column and the predicted output column, 34 times the zeros are correctly identified as zeros, and 33 times the ones are correctly identified as ones, and 5 times, can anyone tell 5 times what happened actually? Ones are identified as 0 or zeros are identified as 1?
Ones are
Ones are
identified as
identified
zero.
as
Zeros.
Ones are identified because this side, as I told, when I have written in the board itself, I have written with respect to the sklearn confusion matrix format only. So this side is actually actual side, and this side is predicted side. Of course, predicted side it is showing in bottom, but anyway, that vertical side is the predicted side. This horizontal side is an actual side. So which means 5 times the ones are identified as zeros, are predicted as zeros. So similarly, 8 times the zeros are predicted as 1. Now the question is, what is 1 and what is 0? Right. So in this data set, in the code book, it has been given like ones are
Getting
admitted and zeros are not admitted. Ones are admitted and zeros are not admitted. So again, it is up to you. So you want to define everything with respect to the admitted case, right? Yes or no? Yes or no? So you say, if I want to speak about this model in terms of recall, in terms of precision, something like that, I want to speak like what is the chance that he will get admitted, what is the percentage of chance that he may he will get admitted, what is the like that. So everything, whatever the inference that I will tell with respect to this model, I will tell with respect to that admitted case, right? Yes or no?
Yes, sir.
Yes, sir.
So I can consider this admitted case as positive and not admitted case as negative. Not admitted case as negative. So once I consider this admitted case as positive and not admitted case as negative, now can you tell me with respect to this matrix, say I'm just keeping this, once again I'm just printing this. This is just for visual. I'm just also computing this in one variable CM. So this 34, 33, 8, 5, and we understood that 34 is the 0, 0 count, and 33 is 1, 1 count, and 5 is 1, 0 count, and 8 is 0, 1 count. Now, can you tell me what is TP?
33.
Consider that 1 is positive. What is TP?
33.
33.
So this box is TP, right? Everyone agreeing this?
Yes, sir.
So, but whenever while I'm writing there in the board, I have marked this top box as on TP. Can you understand that why I'm suddenly writing this box as TP, not this box? Please let me know if you have a doubt over it. Because previously, say let me print this and paste it in. See, here the thing is, this one we are going to consider as negative, this one we are going to consider as positive, and this one we are going to consider as negative, this one we are going to consider as positive, which is different from the way that I have constructed the confusion matrix previously. Yes or no? Previously I have considered this as positive, this is negative. That is the reason why I have marked this box as true positive, this box as true negative. Now as I'm just constructing, I'm considering because as Python is showing me like this is 0 count and this is the 1 count. So I have to alter my inference, right? So now this is my true negative because 0 class is negative class, non-unbidded class or negative class to me. So I'm just considering this is true negative, this is true positive. So I'm just considering this one as false negative and this one is false positive, right? So now with respect to this, I'm just going to define those. So TP is CM of, can anyone tell what is an axis?
Sir, can you repeat once again the TP that that part I did not get?
Here?
Yeah.
See, previously I have given something like cancer, non-cancer.
Mm-hmm.
And I'm explaining it. I have mentioned this is cancer, non-cancer, cancer, non-cancer. So this I have mentioned, cancer case we consider as positive and non-cancerous case that we consider as negative. Yes or no?
Yes, sir.
So in this format, with respect to this format, the first row I'm just alerting for positive case and second row I'm just alerting for the negative case. With respect to this box is TP, positive TP. This box is TN. This box is, this is actually positive, but wrongly it has been predicted as negative, so it is false negative. This one is the false positive, right? So the same difference only here also, but the only thing is the position of positive and negative has been changed. Here the first row is negative. This is not admitted. Here this is admitted. So as this not admitted case, I'm just considering as a negative. So negative, negative, I'm just considering as true negative. This positive, positive, I'm just considering as the true positive. Got the point?
Yes, sir.
Any doubt still?
No.
Yeah. So now CM of 1, 1, right? True negative is CM of 0, 0, right? And FP falsely positive. Can anyone tell index position?
0,
0, 1, right? And FN 1, 0, right? So I have computed TP, TN, FP, FN. So using this, you can compute accuracy, ACC. So what is the formula? TP plus TN, the whole divided by everything. TP plus TN plus FP plus FN. So accuracy is 83.75%. If you want to play with 100, you can now multiply. So accuracy is 83.75. So recall formula TP divided by
EP plus FN.
EP plus FN. You want here itself, I'm just putting. My recall is 86.84 for this. Similarly, I can found precision TP divided by TP plus
FP.
FP and precision is 80%. So whatever that we have discussed, these three things have done now. But I want some kind of balanced measure between precision and recall. So precision is talk about the impact of false positive on my model, and recall is talk about the impact of false negative on my model. I want some kind of balance measure because ultimately I want both the things to be low. I want precision also to be low. I want false positive also to be low. I want precision. I want false negative also to be low. In other words, I want precision also to be high and recall also to be high. So for that only, there is one another measure is there as F1 score. So this F1 score is the harmonic mean between your precision and recall. So harmonic means, you know that 2 times of the two measures. So recall and precision, the whole divided by recall plus precision. So this is the formula for F1 score. So F1 score will tell you the balance, harmonic balance between your precision and recall. So rather than taking arithmetic mean, why we are taking the harmonic mean generally? What is 1 in F1 score? Which one you are talking about, Raghu?
I think 1 in the F1.
F1. It's a name.
That is statistically, there is some other measures also like F2 and other things, but here we are using that F score generally. So, but there is some different variation of that F scores. So that is the reason why it has been labeled. But anyway, here with respect to SQLN, we don't have F2, something like that. But that concept is there. So I'm not very much sure about that statistic part of it. But F1 score, let me explain. Say we have recall of 10% and precision of 90%, right? So recall is actually a kind of measure which is sensitive to false negative. Precision is the kind of measure which is sensitive to false positive. But I want both the things to be high, both recall and precision to be high. But my model is having this kind of characteristics. So I need one kind of balance measure to talk about the overall effect of my model in terms of both false positive and false negative. So we are using the F1 score for that balance measure. Now the question is, if I want to find some kind of balance measure, average measure between two entities, I can go with the arithmetic mean. If I go with an arithmetic mean, what is the formula or what is the value that I will get? So 90 plus 10 divided by 2, I will get 50. So it's 50%, which means, okay, my model is doing well about 50%. That is a kind of analogy that we are getting. So it's a kind of between false positive and false negative. It's a kind of balance effect, something like that we will be wrongly understanding. So that is the reason why F1 score has been computed as harmonic mean of these two measures rather than just an arithmetic mean. If I compute in terms of harmonic mean, then I will be getting like 2 into 90 into 10, the whole divided by 90 plus 10. Can anyone tell what is the value for this? 180,800.
18.
It's only 18%, right? So your harmonic mean will give the performance, overall performance score kind of biased towards the low performance, right? So here, even though recall is 10 precision is 90. If we go with an arithmetic mean, it just gives that 50%, which means a kind of good score. But really, it's not a very good model. That is what we are seeing here in terms of harmonic mean. It's only 80%, 18%. It's only 18%, which means one measure out of these two measures, one measure is actually really low. One measure is actually really low. So when we will, so if I use harmonic measure, harmonic mean, and which in which situation I will be getting 50?
Balance class.
So if almost both recall and precisions are actually close, but still it is around only 50, right? Recall is also around 50 and precision also around 50. In that scenario, I will get F1 score also around 50. But if one measure is very high value, the another measure is actually very low value, then F1 score won't give that exact mid balanced value. It is actually gives the value which is towards the low value out of these two. Here in this case, recall is only 10% and precision is 90%. Now I'm just getting the F1 score is only 18%, which actually talks about the overall quality of the model, both in terms of false positive and false negative. It is not actually really doing well. It's only 0.18, 18%. Right? So that is the reason why F1 score has been computed with respect to harmonic mean rather than just considering the arithmetic mean. So here we are getting 83%. It's well and good, which means both precision and recall, it's actually close to this, right? So it is not that there is not much of difference between the precision and recall. So in terms of handling the false positive and in terms of handling the false negative, my mission is doing the same quality of work, right? It is not like my mission is doing well in terms of false positive, but it is not doing well in terms of false negative. Such a kind of scenario is not really exist. That is what here we are seeing. So we can see recall precision is 86, 80. It's not that much huge difference. So here we are getting F1 score in the kind of mid between these two, 80 and 86, so around 83. So in this case, it's look like a kind of exactly in the kind of mid, simply because the deviation between your precision and recall is not more. If precision and recall deviation is more, the difference between precision and recall is more, then that F1 score will take some value close to that lowest value. If recall is low, then with just near to some recall, some value has been assigned to F1 score. So that is the reason why we are actually using the harmonic mean for F1 score rather than arithmetic mean. Right? So now,
one
yeah.
question.
Yes.
Like, so when to apply F1 score? Like when there is a huge deviation between precision and recall, or when there is no much difference? Because F1 score is well influenced by the deviation between precision and recall, right?
Yes. So which means, say, if F1 score you are getting anything, say if you are getting high F1 score, what is the meaning?
Which means either precision or recall. I mean, both precision and recall both are close
exactly.
to each other.
So yeah, so both are actually doing good. Your precision, your F1 score is also will be high. So F1 score is just a kind of one measure through which you can understand both precision as well as recall. Otherwise, without using the precision or F1 score also, you can see separately what is recall and what is precision. So say in some kind of situation, you want both precision and recall to be kind of high. Say some domain where you are you want the correct output, right? So irrespective of false positive or false negative, you don't have any kind of bias like I want to identify the false positive also correctly, and also I want to identify the false negative. In this kind of scenario, while tuning your model, so with respect to what parameter I want to achieve good performance, that time you can use F1 score, because if you achieve good model with respect to F1 score, then it means that both precision and recall, your model ability to handle both false positive and false negative is good. Got the point?
Okay, got it.
Right. So overall, if you want your model to handle everything perfect, then you have to focus on F1 score, how to improve the F1 score. But sometimes you can't improve the F1 score beyond some limit, because what happened in the sense, if you try to improve the false positive, then automatically false negative will come. If you try to improve the false negative, automatically false positive will come. So if you want to identify everyone, if you want to identify all the cancer patients correctly, you will do some kind of modification with respect to that wrongly identified cancerous cases. You are trying to identify that wrongly identified cancerous cases as correctly as cancerous. Then slightly what happened in the sense that non-cancerous patient also can be identified as cancerous. So which means in the focus of improving the false negative, you are letting some false positive come into your model. The vice versa, all things also will happen. So you can't really improve the F1 score beyond some point really for a kind of a complex real data set. So that is the reason we have measures separately also as recall and precision. So you can try to if you improve the F1 score to the very maximum value, well and good. If not, then you have to focus any one measure, whether recall or precision, to improve it further. Can we check GM, sir? Durga, what do you mean by GM?
So geometric mean.
Geometric mean. Yes, sir.
Yeah, this is geometric mean, right? So this is the formula for geometric mean, right?
Square root of we have to find square root now, sir. This is harmonic.
Oh, sorry. I have yeah, of course it is harmonic mean. So I have told geometric mean. So sorry for that. So I'm just reiterating here by typing it. So F1 score is the harmonic mean between your precision and recall, and the formula is this one. Yes, please make a note of it. So that this formula that I have written is for harmonic mean. I think in a flow I have just mentioned that as a geometric mean. So it is not actually. Yeah.
You mentioned the harmonic mean only, but the question is there anything which we can use with geometric?
No, so there is no meaning. Again, geometric mean is going to give some kind of a balanced effect only, right? So it is not actually is going to give that biased effect. Only the harmonic mean is going to give that biased effect between two parameters. So if you are traveling between 2 points with that, so while you are going, while you are traveling from point A to B, you are going in one speed, and while you are coming back from B to A, you are coming in one another speed. And if you want to calculate some kind of what is average speed or distance covered in that kind of situation, we will be using the harmonic mean, right? So it is kind of overall effect which is actually which is actually impacting on that whole process. Here the same thing. So precision is high and recall is low. I want to bring some kind of balanced effect between these two things. So obviously I have to use the harmonic mean because I don't want to just tell some kind of balanced number, because that balanced number has been misunderstood, like as because of one value is high, my balanced arithmetic mean could have been a little bit high, but it doesn't mean that my model is doing well. So I have to speak the fact properly with respect to both the measures. So I'm just actually penalizing my value of F1 score towards the low value. So for that purpose, we are using the harmonic mean. So as of now, with respect to geometric mean, we don't have any measure. Just if you want, you just compute it and see how it is actually differ from your arithmetic mean. Arithmetic mean is simple average. Harmonic mean is this one. You just compute geometric mean and see how that number is getting different from these two numbers, so that you may get some kind of idea from it. Right. So this is about this 4 measures: accuracy, precision, recall, and F1 score. So quickly, I will just show you one another metrics from sklearn dot metrics import classification report. So if you just print this classification report, that same y-test comma y-pred, you will be getting all the answers. You'll be getting all those values. Can anyone tell what all these values are? As of now, we have calculated one precision. Now it is actually showing two precision. What it actually means?
One for 0 class, one for 1 class.
So what is the precision we got? 80. And what is the recall we got? 86.84 and 83.5 as an F1 score. So that numbers are this numbers, right? Yes or no? Whatever the number that we got, it's the one that I have highlighted, right? Yes or no?
Yes, sir.
So then what is the top number?
It's considering other way around.
Taking non-admission as positive.
Exactly. Non-admission has been concentrated, which means we have computed these two numbers by considering the one class as positive class, admission class as an positive class. Similarly, you can do the analysis by considering the non-admission class as an positive class, right? So if you consider non-admission class as a positive class, with towards that, this is the score. Towards that, this is the score. But we actually computed through the formulas by considering the admission case as a positive case. So with respect to that, these are all the numbers that we got through formula. Now this numbers we can also get it through this classification report. And also this classification report have this ability to consider the other class also as a positive, and it is giving those numbers with respect to that too. And what is the support? What is the support? Any idea?
You count that overall count.
Iteration.
Overall count in the y-test. So this actually, which means in the y-test, 42 observations are belongs to 0 class and 38 observations are belongs to 1 class. 38 observations are belongs to 1 class. So this result it is telling with respect to 38 observation, and this result it is telling with respect to 42 observations. So that is what it giving you. And here you can see why accuracy is only one value. Is it possible to find the accuracy for 0 class and 1 class?
Be same.
It should be overall. Yeah.
So it should be overall, right? So we are considering both true positive as well as true negative, right? Even even in 1 class, true positive is 1 class and the true negative is for 0 class. Even if you just once again compute it, the same value only you will get. So there is no point in computing this accuracy for each and every class, because it is actually using both true measures in the numerator. So now, what about this micro average and weighted average? Here in this case, both are actually coming same because of this number, but micro average is simple average of these two, right? So that is 0.87 plus 0.80 divided by 2. Similarly, recall macro average is 0.81 plus 0.87 divided by 2. Whereas this weighted average is, any idea what would be the weighted average?
The ratio of the both the class and
yes. So it is like 0.87 into 42 plus 0.80 into 38, the whole divided by 42 plus 38. Got the point?
Sorry, can you repeat for weighted average?
Let me write it, otherwise.
Yeah, yes, that is better.
Also for the macro average.
Yeah, macro average is simple. Let me write that. Let me write both. See, macro average is simple sum. So this number, formula for this number is 0.87 plus 0.80 divided by 2. These two numbers, I'm just summing up and I'm dividing that by 2 because only 2 classes, 2 numbers, zeros and 1. So that is actually macro average. And this weighted average is like this, 0.87 into 42. Why 42? This 0.87 precision has been achieved or computed by analyzing this 42 samples with respect to this 42 samples. So 0.87 into 42 plus 0.8 into 38. 0.8 into 38 because the weight of that is 38 sample. The whole divided by 42 plus 38. So this is the how the weighted average will be computed. Got the point? Who asked this?
Yes, sir.
Yeah. Right, and also separately you have a measures, right? You no need to actually always type this formulas. Like we have here we have called the confusion matrix, right? So if you type it ACC, you can see something like accuracy score. Within accuracy score, if you just pass your Y test and Y pred, you can get it. Similarly, you have recall score. Similarly, you have precision score. Similarly, you have F1 score, right? So all those things separately also directly using this function you can compute. It is not like you have to find you have to just compute this TPTN, FPFN always. But doing that TPTN, FPFN, computing it and doing it will give you the clear understanding, right? So always try to do that, compute those TPTN, see the confusion matrix and see whether which one is true positive, which one is true negative. Then on top of it, compute all those measures. That is always a good practice. But anyway, all those functions are available. Using that also, you can compute this. But anyway, quickly, if you want to see some results between all the classes, classification report is one cool thing. So quickly, you can see this classification report. So one another famous measure for all the classification algorithm is ROC curve. So receiver operating characteristics curve, people will call. So this ROC curve is basically a graph between true positive rate and false positive rate. True positive rate and false positive rate. So before going into it, I want to ask one question. What is the relation between true positive and false positive? If false positive increase, what happened to your true positive? What is the relationship between true positive and false positive for any model?
So indirectly proportional.
Negatively correlated.
Inversely related.
So every one of you are thinking or telling like if I increase the false positive, the true positive will increase or reduce?
It will decrease, sir.
It will decrease.
See,
it will increase.
So we have already saw an example when a recall failed. Can anyone recollect that example? In which situation recall measure fails really?
Spam.
No, that is actually general. But after doing the recall, I have given one example.
When false
In that
positive
case,
is high.
got a recall as 100, but even though it's a poor model.
When false positive is high.
False positive is very high, right? Which means, say, my job is to predict the cancer. I'm telling that everyone is cancer. My job is to build the model to predict the cancerous nature of 1,000 patients. I'm just telling that everyone is having cancer. Then obviously my so in this case, what do you think about the true positive? True positive will be low or high?
Low.
Very high.
Very high, right? Say my job is out of 100 people, how many are having cancer? I need to predict. Actually, see, only 95 are non-cancerous, only 5 are having cancerous. But now my algorithm is saying that everyone is having cancer. So which means my false positive is very high, right? Yes or no? If my model predict that everyone is having cancer, my false positive is high. Everyone agreeing this? Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
What about others? Please have clarity over it, because I'm just telling that everyone is having cancer. So the 95 cases who are not having cancer, I'm telling that now they are also having cancer, which means falsely I'm just branding them as positive. Falsely I'm just predicting them as positive. So false positive is very high, right? So because of this false positive is high, do you think that my true positive is also high? Because as I'm telling that everyone is cancer, then obviously this five true cases, or that's 5 positive cases definitely will predicted as positive case, right?
Yes, sir.
Yes, sir.
Correct.
See, please watch this point carefully, because every session I'm getting this answer only. But of course, we always think like false positive increases means true positive reduce, but not really. If I'm telling everyone is having cancer, everyone is positive, then obviously the real positive cases will correctly identified as positive. That I can't expect any kind of misclassification to happen in true positive case. So generally, if false positive is keep on increase, definitely true positive also will increase, right? But I can't consider that as a good model. My true positive increases because my false positive also increases, in the sense I won't consider that as a good model. When I will consider a model as a good model, my model is actually identifying all the true positive. My true positive is high with very low false positive. Then that is a good model. I want my true positive to be high with very low false positive. With very low false positive, then this is a good model. But if true positive is high because false positive of my model is also high, means then I won't consider this as a good model. This is actually bad model. Are you getting my point?
No, sir.
See,
so both the positive thing is actually a good measure, no? Like it is giving a true result. So
see, yeah, I can say, listen. Say here, my data set is like 100 patients are there. Out of that, 95 are non-cancerous, 5 are cancerous, right? 95 are non-cancerous, 5 are cancerous. Now say, I'm just building my model such that my false positive is keep on increasing. My false positive is keep on increasing. So what is the meaning of that? My false positive is increasing, or my false positive is high. With respect to this model, can you tell what is the meaning of false positive is high?
When we take the cutoff point lower than 0.5, in that case.
Oh yeah, I will come to it. But simply
Correctly classifying as
respect to
cancerous.
this, if false positive is high, means are you thinking like there are so many negative cases which are correct, which are actually classified as positive cases? That is the reason why false positive is high, right? Yes or no? Who raised this? Someone asked this, right? Hello, am I audible, right?
Yes, sir.
Yes, sir, you're audible.
I think Sanjay wire.
oh, sorry, sir. I'm in mobile, so
Okay.
call I have to. Yeah.
Okay. So the thing is, say if false positive is high, which means so many non-cancerous cases also will be identified as cancerous by my model. So in that situation only false positive is high. So in that, so if false positives keep on increasing, in the sense, obviously my true positive cases also will be identified by my model as positive, along with all the non-positive cases also my model will be considered as positive. So if my false positive is really high, then it means my model is actually telling everything is positive. Say that is the worst case. In worst case, out of 100 cancerous patient, I'm just telling that everyone is having cancer. If my model is making such a decision, is there any chance that my truly positive cases to misclassify? No, right? All my truly positive cancerous cases actual cancerous cases will definitely identified as cancerous by my model. So, but that is not because of my model ability. It is because of my model is actually wrongly declaring every observation as positive case. In that process, the true positives also correctly my model identified as positive. So that kind of a scenario I don't want. I want my model to predict all the cancerous cases correctly as cancerous without declaring the non-cancerous patient as cancerous. Are you getting my point, everyone? So yeah, so that is what the thing that we are looking for. So say if I'm plotting this, say if I'm plotting a graph between true positive rate and false positive rate, say if my graph is like this, and say this is false maximum false positive rate, say 100%. What your comment about this model?
Worst model.
It's a worst model because at this point I'm achieving the maximum TPR, right? My model is predicting all the positive cases correctly as positive, but at this point if I see what is my FPR is also high, right? So my model is actually predicting all the positive cases correctly as positive because my model is actually predicting everything as positive. There are so many false positive that actually increase my true positive. So I don't want this kind of scenario to be in my model. I want the scenario like to be like this. Just watch this blue line. This is the ideal ROC curve. Watch this blue line. So my TPR has been achieved to the high value of 100% at what value of FPR? For which value of FPR my TPR is higher?
0%.
0%.
Right? So while my FPR is 0 here, that time itself my TPR is 100 and stays 100 throughout. So which means my model is actually predicting all the positive cases correctly as positive, even with without predicting any prediction wrongly as positive. Wrongly as positive. So without saying any non-cancerous patient as cancer, my model have the ability to predict all the cancerous patient correctly as cancer. Got the point, everyone? Yes or no? Anyone want me to repeat this?
Sir, you mean the upper line you are interfering, I mean interpreting currently?
Say say this point. So with FPR equal to 0 itself, I'm just getting the TPR as high, right? Say let me draw one another graph so that you can understand.
Yeah.
What about this model? Compare this model with the blue model. So this model is actually achieving the high TPR, say here. With this FPR, say here FPR could be around say something, right? So which means by my model is predicting all the positive cases correctly as positive by allowing few wrong prediction, by allowing few negative cases as positive. It is also predicting all the positive cases correctly as positive. So I want this peak to be happen with the less FPR value. So more the graph. So this is the ideal. This blue one is ideal. This is okay, fine, good. Also, I can say this is actually poor. Right? So my objective is I want to achieve the high TPR with low FPR. I want to achieve high TPR with low FPR. So by comparing these three curves, this blue curve is actually achieved the high TPR with low FPR because with FPR 0 itself, the TPR is 1. Whereas here for this orange curve, this TPR has been achieved here by allowing some FPR. But here for this red, but my TPR is actually high. At that point, my FPR is also completely high. So which means it's a poor model. People will call this as a kind of random model also. random model, coin toss model. We will call this as coin toss model. Coin toss model is not actually predicting anything by its intelligence. Just like that, it is telling it's positive, it's negative, head, tail, something like that. Just by a luck, it is actually doing this stuff. Got the point now?
Yes.
Everyone?
Yep.
Yeah. So now this is graph, but tell me one thing: how it is possible to draw this graph? How it is possible to draw this graph? Say for a given data, if I ask you to compute TPR is nothing but TP divided by TP plus Fn, and FPR is FP divided by some formulas in the same way. So if I ask you to compute TPR and FPR, you will end up with only one TPR and only one FPR, right?
Yeah, so sir, here we calculate FPR and TPR for each threshold point.
Exactly. So that sklearn is actually giving that true positive, false negative, all those things with a probability threshold of 0.5. So whenever, if it is more than 0.5, it is giving that as one class. If it is less than 0.5, it is actually telling that as zero class. Now for different probability, they are plotting it. So between 0 to 1, so when probability is 0.1, what is the confusion matrix? With respect to that confusion matrix, they are calculating TP, TN, FP, Fn. With respect to that, they are calculating on TPR, TP1. So each and every point in this graph, is for different thresholds. It's for different thresholds, and they are, by connecting all those points that they are achieved for different thresholds, and they are getting this graph. So how to do it? We are going to do it in Python now, right? So say once I got the graph, how can I quantitatively measure the quality of this graph? So it is, I have to see, say, by seeing this, I can tell this blue graph is better than this orange graph, and that orange graph is better than this red graph. But quantitatively, how can I define as the area under the curve? Between these three curves, under which curve the area is high?
The blue one.
The blue one.
Blue one. So that whole region has been covered, right? But here, if you see the orange curve, this area is not covered. But here, with respect to this red line, half of the area has been covered, half of the area is not covered. So the kind of worst value that ROC curve that is that we will calculate as we will notate that as AUC, area under the curve. So that we are actually deriving from ROC only, but that we will be calling that matrix as AUC, area under the curve. If area under the curve is 0.5, what is your take on it? Still you think that, okay, 50% my model is doing good?
Oh, it's the red line.
It's a red line. So which is some poorest of poor model. So you should not consider, right? So for AUC, always you want value to be more than 0.5. So anything less than 0.5, it is a kind of poorest of poor. Anything equal to 0.5 itself, it's a poor model. Just it is predicting randomly. Just it is actually predicting the positive cases correctly as positive, because it is actually declaring everything as positive. So that is the reason why it is actually predicting the positive cases. So such a kind of model that we don't want at all. So ROC, AUC value, we always want to be on the higher side, definitely more than 0.5. So at least we want something more than 0.7, so that we will get this orange graph kind of sort. So if anything close to that blue curve, it's well and good. But anything close to that red line is an indication of poor model, right? So now let me take you how to plot it. So in order to plot this, we want that predict proba. So we have calculated that, right? Yeah. Um, is Lena is here or?
Yes, sir. Yeah.
Lena, can we take break after just 5 or 10 minutes? Are you?
Sure.
Do you have any other class?
No, sir. I thought by that time I load the poll questions too.
Yeah, you can load it now. I will finish this demonstration part of this ROC curve so that we can have a break and we will start with the first topic after.
Fine, sir. Yeah.
So we have this mod log model that we have defined through logistic regression SQL and package. And yesterday itself we have saw this predict proba. So predict proba is actually another bracket. So predict proba will actually give you the probability values. So the first column talks about the what is the probability that particular observation belongs to 0 class, and the second column talks about what is the probability that that particular column belongs to 1 class. So now we are going to concentrate on only 1 class. So what I'm doing here is say I'm just keeping this as prob, and I'm just calculating something like prob underscore 1. That is the probability of 1 class. This is nothing but the value given in the second column. So colon comma 1. So I'm just taking the second column alone, and I'm just considering that as probability of 1 class. So if you want to just print and see prob underscore 1 of colon 5. So we are getting that only one row of data. Previously we used to call it as we used to get it as 2 column of data, no? So now it is only one array. Previously it is 2 column of array. So now I'm just loading that function from sklearn.metrics. We have ROC curve, and also we have ROC AUC score. Both I'm just loading. So this ROC curve will have the ability to compute the TPR and FPR value for different thresholds. We don't need to again loop it in some for loop for different threshold values. This ROC curve will have the ability to compute this for all the different thresholds. Randomly it will take different threshold value, and it will compute the FPR, TPR by constructing a confusion matrix and all those things internally. So only thing is we have to properly call it. So ROC curve of the same thing, my white test, comma, rather than giving wipe red, I have to give the probability. So probability of class 1. So probability of class 1 I'm just passing. So this ROC curve will throw out 3 information. One is false positive rate, that is nothing but our x-axis, and the other one is true positive rate, that is nothing but our y-axis. And the third information, it is also give us threshold values. So what are the different thresholds for which it's computed that FPR, TPR value. So that also it will give to us. So I'm just running this. So now it has been computed FPR and TPR. Then it is simply a plot between FPR and TPR. So this is my ROC curve. This is my ROC curve for different value of thresholds. So it's like it's shaped like this. Obviously, it is not a very poor model, right? Because it is that it is much close to my ideal, not actually close to my random model. So in order to just get some kind of more inferences, just for the sake of your reference, what is x-axis and y-axis, and I'm just giving that x label is false positive rate, FPR. FPR is also known as 1 minus specificity. 1 minus specificity. Similarly, plot dot y label, but your TPR. TPR is also known as sensitivity. So it's just what is that x-axis, what is that y-axis that we are printing. So if you want to see what is the area under the curve, so which talks the quality of this curve quantitatively. Of course, by seeing this curve, I can find, okay, it is close to kind of ideal, it is not too poor, something like that. But anyway, if I want to know what is that exact area which is covering, how to use this ROC AUC score of y test comma prob 1. So 0.94. So 0.94 is a good AUC score, right? So it is in terms of predicting the true positive with less false positive, it is doing well. It is doing well. So ROC score, ROC AUC score will tell the ability of model to predict all the positive cases with less false positive, right? So ROC score of 0.94 is a kind of reasonable good score, which tells that my model ability to predict the true positive case with less false positive is good enough, right? So with this, I think you can take a poll now and you can go for a short break.
Sure, sir. So loaded the poll questions. I hope it's visible, class.
Yeah, yes, yes.
Can you just scroll up a bit?
Myself?
Python notebook, yeah.
See, specificity, I am just writing the formula. Don't wonder what is specificity. Specificity is another measure which talks about the quality of predicting the negative cases. So true negative divided by true negative plus false positive. That is actually specificity. We know sensitivity or true positive rate and recall, everything is same. That has been given by the formula true positive divided by true positive plus false negative. You just ulta it so that what is the ability of my model to predict the negative cases correctly. Then you can use specificity, in which for which the formula is true negative divided by true negative plus false positive.
So a little bit more. Can you just scroll up?
Sorry, did we change something, sir?
Sorry?
No. What to reverse? Did we
No.
reverse?
Say, you know what is sensitivity formula, right? Sensitivity, recall, TPR, everything is same.
Correct.
Even I can write recall also here. So all are same. What is the formula for that?
For recall? TP by TP plus F.
TP divided by TP plus F1. So what is the meaning of it? It is the ability to find the positive classes, right? How good my model in predicting the positive class. So sorry. Similarly, there is one measure like specificity. That specificity is nothing but it tells how good your model is in predicting the negative class correctly as negative. So the same formula, only thing is whenever P, you have to change that as N. Whenever N, you have to change that as P. So TP divided by TP plus F1 has been changed as Tn divided by Tn plus Fp, so that you can call that as specificity, which talks about the model ability to correct to identify the negative classes correctly as negative. Please everyone answer that poll question too. Rina, at what time we can resume the session back? 11:50?
Sure, sir. 11:15.
Hi, shall we start? Is everyone here?
Yes, sir.
Shall I end polling, sir?
Yes, Lina. Actually, I don't have a provision to see that polling. So-
Yeah, I put the snapshot in the WhatsApp, sir.
Okay. Let me check that.
Yeah, 3 more responses. If I could get, we'll get 100% voting.
Okay.
Lina, this is Bharat, Jia Bharat. I just submitted. So I had some connectivity issues, so I just submitted the poll from my end. Yeah, just
Great.
now I did.
Thanks.
Yeah, thank you.
So the first question is accuracy score. That's the answer. Second question. Yeah.
Lena, can we just see it on the screen, the question and then?
Oh yeah, sure. Shall I end the poll then? I think, yeah, sure. Just share the results. Third question is about, second question is about which of the following can be called as false positive. So actual value is 0 and classifier predicted it as 1. Third one is precision is sensitive to false positive. And fourth one is which of the following statement is true about increasing the classification threshold. So here I got around 50-50 as the polls. So increase the false negative is the answer.
Yeah, but Lina, that fourth actually I yet to discuss. Of course, they can answer it with that understanding. But anyway, now only we are going to discuss that. I thought of discussing that before the poll. But anyway. But I wonder why for the first question, some of the answers are F1 score. Any doubt over that? Which of the following measure is not a good measure for imbalanced data? I'm seeing some answers with respect to F1 score. So any confusion over it? As because I have told like F1 score is a kind of balanced measure between precision and recall. Any queries or any doubt?
So maybe we have not connected accuracy to the F1 score. I mean, in interpreting.
Yeah, you can't really connect accuracy to F1 score, right? So F1 score deals with only precision and recall, right? If you see the F1 score formula, the formula is 2 into precision into recall, the whole divided by precision plus recall. So it is actually going to give some kind of harmonic balanced measure between your precision and recall. So obviously precision and recall are the measures we will go when our data is imbalanced. Because if our data is imbalanced, then going with accuracy is not actually good. We have saw that. So with that example of 95 people having cancer, not having cancer, and 5 people having cancer, even though my model is predicting only 2 people correctly as having cancer, my accuracy score is giving me very high value. But if I see my recall value is low. So in that sense, for an imbalanced data, I will definitely not go with accuracy score.
Yes, recall is an enhanced version of accuracy.
Sorry?
So accuracy only is connected to recall. Is that it? So
see, recall and precision are actually talks about how your model is sensitive to false positive and false negative for each class. But accuracy is actually talks about overall what is your model capability to find all the classes. Your model quality to find or identify or predict all the classes has been modeled through accuracy. Say your model is actually doing well with respect to one class, but your model is not doing well with respect to the other class. Say your model is actually imbalanced, like 95% of data is non-cancer and 5% of data is cancer, your model is doing well in terms of predicting the cancerous, non-cancerous cases, but your model is not doing well in terms of predicting the cancerous cases, but still your accuracy could be very high. Still your accuracy could be very high. Even though your model is not at all predicting one class well, your accuracy score could be very high. So that is the reason why for imbalanced data, we should not go with accuracy score. We have to see the other measures. Right?
Yes, sir.
Fine. So now we are moving into how to improve the model quality. So now we have measured our model quality in terms of different measures. So now we are going to do something to improve its quality further, right? So anyway, this data is all.
For the last question, can we discuss?
Yeah,
threshold?
now by doing this itself, we can discuss that.
Okay.
Right? Because I thought of finishing this, somehow I missed it. So to improve the quality of the model, one thing is I have to do some kind of adjustment with respect to false positive and false negative. Say our sklearn package, as I told, is have the ability, it actually consider the threshold value as 0.5. So anything more than 0.5, it's considered as class 1 or 1 class, and anything less than 0 means it's anything less than 0.5 means it's considering as 0 class. But what happened if I change this threshold from 0.5 to 1 fro? If I increase this threshold, what happened? If I reduce this threshold, what happened? How it is affecting the different performance measure of our model. So that is what we are going to discuss now, right? So for that, quickly, let me take different threshold values. EH, which is equal to, say I'm just taking like 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, right? So from 0.2 to 0.8, I have taken different threshold. And I'm just running this in one for loop. Like for each and every threshold, I'm just going to compute all those measures. For each and every threshold, I'm just going to compute what is recall, what is precision, what is accuracy, what is F1 score, and what is the ROC AUC score. So for that, I'm just putting this in one for loop, like for I and TH. So once I go in, I have my YPRED 1. Fine. So let me first do it here, then you will get that clarity. We have prob underscore 1. So prob underscore 1 is nothing but what? Everyone have this variable with you, right? Prob underscore 1, which talks about the probability for one class. So with respect to this prob 1 only, your sklearn is making the decision, like whenever this probability value of class 1 is greater than 0.5, it's alerting that to class 1, and if it is less than 0.5, then it's alerting that particular observation to class 0. So now what I'm going to do here is I'm just going to make something like this. If it is greater than 0.6, if it is greater than 0.6, it actually print one true or false matrix. What is the meaning of this true or false matrix? What is the meaning of this true or false matrix? Whenever there is a false,
false one or less than.
False one are less than 0.6 and true ones are greater than 0.6. Now what I'm doing is, now I'm just passing this in one new array. But before that, I'm just creating, say, one YPRED 1. I'm just creating with all element zeros. So np dot zeros of length of y test comma 1. So what this will do, it actually create one complete array of 0 of same size of my y test. So in as of now in YPRED 1, I have everything as 0. I have everything as 0. Now whenever this condition has been satisfied, prob 1 greater than 0.6, I'm just passing this Boolean array as an index to my ypred1. In those position, I'm just changing the value as 1. In those position, I'm just changing this value as 1. Let me print the ypred1.
Sorry, can you just explain what are we trying to do?
What I'm trying to do is, say in prob1, what I'm having, I have printed that initially. In prob1, we have all the probability value belongs to class 1, right? Right. So now sklearn is actually computing this ypred while we are applying the predict function by having the threshold as 0.5. Any probability value greater than 0.5, it is actually making as 1. And any probability value less than 0.5, it is making as 0. Now, deliberately, what I'm doing is I'm accessing that probability value. And whenever the probability value is greater than 0.6, I'm just making that as 1. The remaining thing I'm just making as 0. The remaining logic I have not written because I have initialized one array which is full of 0 of the same length of my y-test. In that place, whenever this probability value is greater than 0.6, I'm changing that particular position alone as 1. So now ypred1 is the predicted value of my model with respect to the threshold of 0.6. Got the point?
So deliberately we are moving the default threshold from 0.5 to 0.6.
Yes, yes. I'm going to see for 0.6 how my model is performing.
Got it.
Right. So this is the syntax with respect to just getting the ypred value, that classified output 0 or 1 value for different threshold. Now I'm just bringing this logic inside this loop. Inside this loop, I'm just bringing this logic. So ypred1, which is equal to np.zeros of thing. So here what I have to change in place of this 0.6, what I need to put. In place of this 0.6, what I need to put?
I.
Yeah, so greater than or equal to I. Even if it is 0.6, I'm just making that as 1. So greater than or equal to I just put it as 1. So once I have this new ypred1 with me, I'm just computing the accuracy. So for each and every threshold I need to compute. No, so what I'm doing is I'm just comprehending this in list. So accuracy, and I'm just going to compute recall, and I'm just going to compute precision, and I'm just going to compute F1 score, and also I'm just going to compute ROC, AUC. So I'm just declaring all those things as an empty list. So in ACC, I'm just appending. So if you remember, I have declared all those functions here. If you want all those things to be computed one by one, so I'm just copy paste for your reference. So you can call accuracy score, recall score, precision score, F1 score, ROC, AUC curve. ROC, AUC curve you might have called, but all the other things I don't know whether you people used it or not, because I have just shown you along with confusion matrix. These are all the functions also available. So rather than seeing all those numbers or computing all those numbers using the formula, you can also individually compute using this function. So I'm just going to use those functions now. So accuracy score of y-test comma ypred1. So now ypred1 is having the predicted output with respect to the threshold of 0.2, because at the first iteration it is 0.2. So similarly, in the next line, I'm computing the recall. For that, I'm just using the recall score. The third line, I'm just computing the precision. For that, I'm just using the precision score. The next line, I'm just computing the F1 score. For that, I'm using the function F1 underscore score. And also at last, I'm just computing ROC, AUC. For that, what is that exact name. AUC. ROC AUC score. So once I compute all those things, so just run this. Yeah, without any error it ran. Let me copy paste it anyway. That window. So I have just computed accuracy, recall, precision, F1 score, ROC, AUC for all the thresholds that I have defined. So once I have all those things, I'm just bringing everything into one report card, say like threshold report. So pd dot data frame of, so th underscore rep of, the first column is accuracy, which is equal to, or first we can put the threshold, because for what threshold numbers are. So th, second number, accuracy. This we have it in ACC. The third one is recall, that we have it in REC. The next one is precision. One is F1 score. The next one is ROC AUC. Just I'm printing this DHL. I just copy paste this report syntax also for your people. So now we have got for different threshold how the accuracy value, recall value, precision value, F1 score value all are changing. So everyone got this report in your notebook?
Yes.
Yes, sir.
Right. Now tell me generally, if I'm increasing my threshold from 0.5 to some high value, so I'm just increasing my threshold above 0.5, what happened to my false positive, or what happened to my false negative? Say first understand what is the meaning of that 0.5. If I'm keeping my threshold as 0.5, then my statement could be like this. If probability of if threshold, if probability of class 1 is anything greater than 0.5, then I'm just going to say class 1. If my predictive probability is anything less than 0.5, I'm just going to say that is class 0. If the probability is greater than 0.5, I'm just going to say that is a class 1. If it is if the probability is less than 0.5, then I'm going to say this is a class 0. So that is what the baseline statement. Now, if I increase my probability threshold from 0.5 to some value, say 0.7, then what happened to my false positive or false negative?
A false negative should go down.
Really? See here, you just see here and tell. I hope everyone got this table now. While we are increasing the threshold, what happened to the recall? In this table, while increasing the threshold, what happened to recall?
Recall will decrease.
Recall is decreasing in the sense, recall is sensitive to what? False negative, right?
False negative is increasing.
So if recall is reducing means false negative is increasing. Is everyone agreeing that? False negative is increasing. So if I'm keep on increasing the threshold, my false negative increase. My false negative will increase. But okay, I'm seeing this. I know the formula. Recall formula is TP divided by TP plus Fn. So I'm seeing that recall is reducing. So Fn is increasing. That is the reason why recall is reducing. Okay, with respect to the math, with respect to the formula, I'm telling that. But why it is happening? Logically, why it is happening? Now, as threshold, I'm just increasing. my room for positive is actually reducing, right? My room for one class is actually reducing it, right? Yes or no? Say initially with respect to the 0.5, say if one threshold is 0.6, it may comes to one class. It may comes to one class, and also it could be the true. Now, as I'm increasing my threshold, say if I increase my threshold to 0.7, even though some probability values are 0.6, 0.65, all those things will come to zero class. But with a probability of 65%, I can tell that it should be in one class. But as I'm increasing my threshold, now it is coming to zero class, because as when threshold is 0.7, what it means, anything more than 0.7 should be comes under class 1. Anything less than 0.7, it belongs to class 0. But which means with 69% chance, I'm just telling that it is, if one probability is 69.69, so there is a 69% chance that it belongs to class 1. But my threshold is 0.7, I'm just saying that it belongs to class 0. Class 0. So ideally speaking, or normally speaking, with some probability of 0.69, it should be deserved in class 1. It may be true also, but now it's going to class 0. So obviously we will expect the false negative will increase if we increase the threshold. So everyone agreeing that? Yes or no?
So not able to visualize. Can you repeat?
So is that the
Let me go to the board.
And we see false positive also is increasing, right? Like based on precision.
Yeah, that is, precision value is actually increasing. If you see, if threshold is increasing, precision value is increasing. If precision value is increasing, means false positive is actually reducing. Right? Let me take you to board to explain it. See, we have a scale like this. This is 0 probability. This is 1 probability. And this is the 40.5. Right? So now, with respect to this, all this R comes under what? Class 1, right?
Yeah.
Whenever a data is here, it is class 0, right? Say this is with respect to the 0.5, your model is doing say 100%, it is actually predicting everything correctly, for example, right? So this is ideally correctly predicting with respect to the threshold of 0.5. Now what I'm doing is, now I'm just increasing my threshold from 0.5 to 0.6. I'm increasing my threshold from 0.5 to 0.6. Now what happened to this? Provided that previously everything has been perfectly classified with respect to that 0.5 threshold, now what happened to the values in this range? Whether it is false negative or false positive now?
So false negative.
False negative.
This is false negative, right? Because now with respect to this threshold, this only it is class 1. All those regions are now, it's class 0. So even though this region is actually belongs to one class, now it has been going to the 0 class. So false negative is increasing. Can you see that now visually? If I increase this further, I'm just increasing the false negative.
Yes, sir.
Right? So similarly, on the other side, if you are reducing the false positive, say if you are reducing the threshold, so from here, say here I'm just coming 0.4, which means now up to this range, it is actually class 1. Only up to this, it is class 0. Which means, what about this region now? What about this region now? It is actually going to the positive side, right? Class 1 side. So this actually false positive side. So now false positive is
reducing.
False positive is increasing.
Increasing.
If you are reducing the threshold, say from 0.5 to 0.4, if I'm reducing the threshold, my false positive is increasing. If I increase the threshold, my false negative is increasing. So that is the reason. That is the reason why in this Jupyter notebook, while we are increasing the threshold, my recall is reducing because it is sensitive to false negative. As false negative is increasing, recall is reducing. On the other hand, precision is actually increasing for the increase in the threshold, because if I increase the threshold, my false positive, what happened? If I increase the threshold, what happened to my false positive?
Will reduce.
Will reduce. So that is the reason my precision is increasing.
Sir, this is the true if I have a perfect distribution of probability, right? What will happen if I have a, can we go to that board? Yeah, so if I just consider this F1 green line, then there might be some misclassified also. So they previously they were known to 1, now they will be known as 0. So which means the class, I mean the just 0 class got which were missed.
No, that green region talks about that previously it is actually 1, now it is actually comes as 0. Right?
Yeah, and it may be like,
provided that previously that while it considered as 1, that is the correct classification, now it is actually wrong classification. That's why we are calling this as false negative.
yeah, but what I'm saying is it may be like actual class was 0, but it had got a high probability, and it was in predicted it was classified as a 1.
Yeah. So that is
then,
the reason. Yeah. So that is an exact reason. Sometime with respect to the 0.5, my performance is not good. By increasing or reducing the threshold, I may get the good performance.
Yeah.
Right. So I'm not saying that. So for the sake of explainability, I told that if with respect to 0.5, I'm getting the perfect prediction. So with respect to that benchmark, I'm just explaining why I'm calling, like if I increase the threshold, how false negative is introducing. If I increasing the reducing the threshold, how false positive is introducing. In order to explain that, I told that with respect to the 0.5, my model is doing good, but it need not to be, as you are pointing out, it need not to be. So now what I'm doing is I'm just exploring my model, say for different value of the threshold, for which value of the threshold I'm getting the good recall, for which value of the threshold I'm getting the good precision. I'm seeing that if I'm just relating that to my domain, if my domain is actually need good recall, my domain want very high recall, then what I need to do? Can anyone take this question? If my domain want high recall, say I'm just predicting the COVID, for that I want high recall. Right? So what I want to do with 0.5 threshold, I'm not getting the expected recall score. So I want to
reduce it.
False negative should be decreasing.
False negative
should decrease.
So for that, what I need to do?
Reduce threshold.
Reduce the threshold.
Reduce the threshold. So it is like, say, even in one simple sentence, I can put it. So previously with the 0.5 confidence, only if 50% probability chance is there, then only I will call, okay, you have COVID or you have cancer. Now, even if 30% of symptom is visible, even if 30% of indication is there that you could have a cancer, I'm saying that you will be having cancer. Right? So I'm there in the safe side. So definitely, I will reduce my false negative. Of course, false positive will slightly increase. Fine. I'm not worried about the precision in this case. I'm just worrying about only the recall. So even at the cost of increasing some false positive, I'm making sure that my false negative is low. Got the point, everyone? Yes, sir.
Yes.
Yeah. So here, anyway, here it is clearly evident, right? So threshold is having, keep on increasing the threshold, you will get reduction in recall. And if you keep on reduce the threshold, you will get then increase in precision. So with respect to that, what is an impact on F1 and FP also, you can easily relate. So likewise, you can see a table like this, and with respect to that, you can take a call, say provided that what is the kind of balance that you want, say with respect to the 0.2 threshold, your recall is very high, around now 0.95, but at the same time, your precision is very low, like 0.72. So you have to see with respect to the 0.5, it is 0.86 and 0.80. With respect to the 0.6, what you are seeing? With respect to the 0.6, what you are seeing?
Bit more balanced between recall and precision.
F1 score is high.
Say with respect to the threshold of 0.5, my recall is 0.86 and precision is 0.80. With a threshold of 0.6, I'm not actually reducing my model is not sacrificing any recall score, but still it is actually improving the precision. Yes or no? And also that because of that effect is reflecting in terms of improved F1 score and also in improved AUC. So rather than having a model with a threshold of 0.5 for this data set, if I use the 0.6 threshold, my results are good. Got the point?
Yeah, sir. How this AUC changing?
So with say how the AUC changing in the sense with respect to this 0.6 threshold, all the true positives are identified as the true positive without allowing more false positive to happen.
Yeah, but for one model, we'll have only one AUC. It doesn't matter. It doesn't depend on threshold, right?
Yeah, it doesn't depend on threshold, but say with respect to this 0.6, it is actually calculating this once, no? So with respect,
yeah, but it doesn't depend on 0 and 1. I think it depends on, because to calculate AUC we are always running threshold cutoff, right?
Yes, of course. Here in this column, for modified threshold, seeing that AUC is meaningless, so you can reduce, right? You can just drop the column, right? So because AUC is a kind of collective measure for all the thresholds, there's no point in actually saying seeing the AUC here. So for how the recall precision F1 score actually behaving for a different threshold, there is some logicality because AUC anyway internally is going to use all the threshold to plot the graph.
Yeah.
Fine. So this is the kind of report that we got. Now, say with respect to ROC curve also we can identify the correct threshold. With respect to the ROC curve also we can identify the correct threshold. So if you remember, ROC curve is actually plotting the graph between our precision and recall, right? ROC is actually capturing the relationship between the precision and recall. Let me draw here. Sorry, ROC is actually capturing the relationship between TPR and FPR, not precision recall, TPR and FPR. Just see your graph is like this. So we discussed like for different thresholds, it is calculating the TPR and FPR and it is plotting this graph. Now, if I ask for which threshold your model is doing well from this graph, how can you identify that? How can you identify the point where the performance is good?
So from where this line is saturating, from that draw a vertical line.
Right. So if I see this point, this is the point at which my TPR is actually reaching the maximum value for the first time. Is everyone agreeing that? Is everyone agreeing that this is the point above which there is no increasing TPR? So my TPR is saturating at this point. Yes or no?
Yes, sir.
So this is, say if I compute what is the threshold for this point, then I can use that threshold as my final threshold for my model, right? Yes or no? Because this ROC curve is actually plotted between the TPR and FPR, but how it is actually arriving different multiple TPR and FPR? by just internally taking lot of threshold values, it is actually again and again constructing the model and finding this TPR and FPR, and it is connecting all those points. Now, if I just compute what is the value of threshold for this point, this could be the good ideal value, which will give me the good performance, right? Everyone agreeing that?
Yes, sir.
But how will we determine that?
Yeah, that I'm going to tell. But are you agreeing that for
Yes.
this threshold, your model is doing well, right? So now how to compute this? How to compute this? How to form one objective function like what is the, is everyone agreeing that the difference between TPR and FPR is maximum here? Yes or no?
Yes.
Point difference between TPR and FPR is maximum. Say
Yes.
my objective is like I have to find the threshold for which my difference between the TPR and FPR is maximum. That is an ideal point. Say what is the worst case? Say what is the value that say if the TPR I want this FPR to be less, I want this TPR to be high. So which means if I find the TPR difference between an TPR and FPR, I want this difference between these two things will be always high. Then that is one indicator that my model is doing well, right? Because
Sir,
yeah,
I mean, that difference remains same for the curve after that point, right? I mean, the difference between TPR and FPR will remain maximum after that point.
no, here FPR value is actually still it's different. No, here
FPR keeps increasing.
if FPR is keep on increasing. No, say if you consider this point, for this point TPR is same, but FPR is different. No, for this point, and all.
Understood, sir. Yeah.
Right. So if FPR is increasing, then difference between TPR and FPR will reduce. No, for this point. So obviously this is the point for which the DPR FPR difference is maximum. So now we need to compute it. Now you got the strategy, no? So for different threshold, I'm just going to compute TPR and FPR, and I'm going to see for which threshold the difference between the TPR and FPR is maximum. That threshold I'm just going to use as a final threshold for my model, right? So how to do it? Simply, I'm just going to, rather than, of course, you can also define threshold in a continuous way, and you can compute TPR, FPR, and you can keep on compute the difference in terms of TPR and FPR. Rather than that, quickly what I'm doing is I'm just using that ROC function itself to do this. Let me quickly take to Jupyter Notebook. See, we already computed, but anyway, I'm just computing once again. FPR, TPR, comma, thresh, which is equal to ROC curve of y test, comma, prob underscore one. But I think prob underscore one I have to run. I'm just taking this once again. So I'm just taking the predict probability, and from that for that one column alone, I'm just taking. For that, I'm just calculating ROC AUC, not score, just ROC curve. For that ROC curve, I'm passing y test and prob one. It will give 3 output to me. I'm typing all those things here. So I'm just using FPR, TPR threshold to receive it. Fine. So now this ROC curve function computed the FPR value and TPR value for different thresholds. I'm not defining the threshold. Automatically, it will take a lot of thresholds. And for with respect to all those thresholds, it's computing the FPR and TPR. So now what I'm doing is, say I'm just keeping some result table, because I want to just put it everything in one table. So I'm just creating one data frame here itself, the 3 column that I want. So I'm just keeping that as the first column is TPR, in which I'm just moving this TPR value, and the second column is FPR, in which I'm just moving that FPR value that I have got it from ROC curve. And the third column, I also want to see the threshold. I'm just moving my THRES value there. So simply I'm just creating one dictionary and I'm passing this. So if you see the table, so it is actually printing all those informations, TPR, FPR and threshold. So anyway, now once I have this table, or once I have this 3 information, TPR, FPR and threshold, I'm just creating one new column in this table as a difference. So difference is equal to table of TPR minus table of FPR. Table of FPR. I have calculated this and I'm just ascending it, because for what is the maximum difference that I want. So sort values, I'm going to sort this with respect to difference and ascending equal to false. So I'm just saying, say top 10. Difference is not there here. Difference.
Left in the first statement, you should not have this a table of difference. You guys have given. No, in that row itself, table of difference you have given. That array should not be there. This in line number 142 only.
I think it's a spelling issue, no?
No.
You are putting table of.
Yeah. Again, yeah. No. Correct.
Oh, sorry. Here, table. This is what you mean, no?
Yes, sir.
Yes.
Fine. So the difference is high when my threshold is 0.6097. Right? So I'm just printing the TPR, FPR value for all the different thresholds that has been automatically generated by that ROC curve function. So I'm just seeing the top thresholds for which the difference between the TPR and FPR is maximum, because I understood from the ROC curve, whenever that difference between the TPR and FPR is maximum, that could be the ideal choice for control for my threshold. So here I'm just getting the threshold value as 0.0697. So can you just include that also here and see 0.0 . or I can simply once again run this here. Comparatively see all those things. I'm just copy pasting this once again. And in that list that we have given, I'm just introducing this also. This threshold. Exactly the same threshold that we are getting. I'm just running. Of course, individually also you can compute, just for the sake of bringing everything together.
Sir, I think there should be a comma.
Where?
In
I've given
threshold.
comma now.
No, threshold. You should see.
Threshold?
Oh, you have taken this big number. Okay, sorry, sir.
Anyway, I'm not seeing any improvement really, even though compared to 0.6, compared to 0.6, 0.609782. But anyway, already that we have assumed that it's 0.6. But with respect to that 0.6, even though that precision recall distance, that is TPR, FPR difference is more there, on this data, I'm not seeing the performance better than 0.6. You can see here, already we got it for 0.6, these numbers. But here,
actually, recall have dropped.
Recall have been dropped. Precision has remained same. I think this is because so every one of you also getting like this. Recall has been slightly dropped. But here we are getting like for the difference is 0.7255 with respect to this TPR and FPR. Anyway, even if so, what you can do in order to check that, here in this table we have recall and precision. Recall is TPR, but we don't have FPR. So you can also include FPR in this. You can also include FPR in this. Say like just using FPR. So FPR dot append, but false positive rate we don't have command. False positive rate we have to compute separately. We don't have a command to append here, but for that I have to compute TP. For false positive rate, the formula is FP divided by FP plus TN. So I'm just writing it and just let this job to you people. FP false positive rate formula is FP divided by FP plus TN, right? But we don't have a direct formula for computing the false positive rate. So you have to internally within this loop, you have to also compute this confusion matrix. And from this confusion matrix, if you compute FP and TN and apply in this formula and then append with FPR, so that you can also create one new column as FPR here and see whether TPR, FPR difference is more, right? Obviously it must be, but anyway, here we don't have FPR column. Precision we have and recall we have. Recall is equivalent to TPR. but we don't have anything called FPR. But this threshold of 0.607 we got for the condition where TPR minus FPR is maximum, right? So even though that condition has been satisfied with a threshold of 0.609, that actually not improving recall. It is actually slightly bringing down the recall, right? But anyway, you have to see these two approaches separately. That approach with respect to the ROC curve, in order to get the get the good results with respect to the ROC curve, we have just applied that concept. That concept is actually known as that FPR minus TPR should be maximum. That concept is actually known as Uden index. So you can also note down that this approach that we have done here, this table, it's actually known as Uden's index. As this data set is not really big and also not really complex, it is not actually producing a better result with respect to the Uden index. So by just applying different thresholds randomly between 0.1 to 0.2, we are getting the good results in terms of precision and recall. But Uden index actually using the concept of difference between the FPR and TPR. So if the difference between the FPR and TPR is maximum, that could be the ideal point with respect to the ROC curve. But anyway, that threshold that we are getting with respect to the ROC curve, here it is not reflecting in terms of recall precision value. So it is about different ways. So you have to see, you have to just like that give different threshold as we did and see what is the precision and recall value, and you can take a call on which threshold you can go ahead. Or you can also use the Uden index, and with respect to the Uden index, you just see what is the threshold that you got. Once again, for that threshold, you have build the model and see what is your recall precision and all those things. If you feel like that Uden index threshold is better than the other way of exposing the threshold, you can go ahead with the Uden threshold. Otherwise, as we did it, you just explore your model for different value of threshold and just take a call on which threshold you can use for your final model. So here, with respect to this table that we got at last, I just go with the threshold of 0.6, even though my Uden threshold is 0.6097, which is actually almost same with respect to the other threshold that we got 0.6. But anyway, that Uden threshold is not really doing well compared to the threshold 0.6. So I can go ahead and freeze my final model threshold as 0.6. Right? So this is two different approaches. You can use this Uden approach, or you can use a simple threshold approach and compare all those measures. So with respect to this, I'm getting good value in terms of recall precision F1 score with respect to the threshold 0.6. So I'm just freezing 0.6 as my final model threshold.
Sir, is there any region that ROC curve is not showing all the threshold points?
Where?
ROC curve table.
Here.
It is starting from, I think.
So it is actually, say that actually mathematically works in a way, even some threshold more than one also it will take. If you just print all the threshold value, some threshold value you may get even 1.44. But anyway, it is equivalent to 1, right? Because that white top, it's not going to be more than 1. So just randomly it is generating all the threshold values between some low number to high number, and it is actually exploring your thresholds. So here, why threshold? Because I have given head of 10.
Yes, actually I see 1.99.
Yeah. Just like that, it will compute all those values. But anyway, for that value of 1.9, whatever that you got for 0.99 or say for ideally 1, that is the same YPRED only you will get it for 1.9 also. So mathematically, while it's doing, it is actually taking randomly all those numbers within some range. We can't really decode it. Of course, in GitHub, you can find the backup script for this ROC curve. If we go through that, we can understand in what way that they are generating those random threshold values. But anyway, for that 1.9 and for that 1, that value will be remain same, right? Because our predict probability can't have any value more than 1. So while it's checking the condition, whether it is greater than 1 or greater than 1.9, that logic not at all, that logic will remain same.
Yeah.
So likewise, you can tune your model with respect to the threshold. And after doing this tuning, we come to know that my model is doing well for the threshold of 0.609782. So that is what the kind of conclusion that we are making with respect to this model after tuning it. Right. So of course we can do other kind of tuning like hyperparameter tuning and other things, but rather than tuning those hyperparameter for this logistic model, we will be exploring that with respect to the decision tree. So how to tune it. So once we discuss that hyperparameter tuning with respect to the decision tree, even you can come back here and you can explore what are all some other parameters you can tune. So you remember what are all the different solvers available for the logistic regression. Yesterday I have briefed, so SAG, SAGA, liblinear, LBFS, so something like that. Different solvers are there. So you can also explore those solvers and whether how different solvers actually, whether by using different solvers, whether my results are changing or not, because this data may be converge very effectively, or that parameters can be correctly identified or correctly estimated for if you use a SAG solver compared to SAGA or compared to liblinear. So you can also explore your model with respect to the different solver. How to do it? So it is very simple. Say you have constructed your logistic regression model, no? So here, see here, we have just given the logistic regression alone. So here you can go to, you can pass one argument as solver, and whatever the solver that you want to apply, you can just give it here and you just compare the results. So while you are giving SAG as a solver, what is your result? If you are giving SAGA as solver, what is the result? If you give the liblinear as a solver, what is the results in terms of accuracy, in terms of precision, in terms of recall? You can once again compare, and for which solver for this data your model is doing good, that solver you can consider as the final model. So if you just go shift tab, and if you see internally, you have Newton CG, LBFGS, liblinear, SAG, SAGA, all those things you can do. Just you have by default LBFGS will be considered as your solver. If you want to change and if you want to see the different performance for different solver, if you just give SAG as a string and if you run, your model will be built with respect to the SAG solver. What is SAG solver? It's a stochastic gradient descent. Yesterday we have discussed the likelihood cost function. So how to solve that likelihood cost function for the minimum value of likelihood. So like that, for achieving that, different mathematics can be used. So different mathematics are available under different solver option. Whatever the solver option that you want, you can apply and see between different solver option whether the results are actually changing or not. So like that, you can explore different parameters that you can pass, that you are allowed to pass within this logistic regression function, and you can come up with what is the kind of final combination for which your logistic regression is giving a very good result. That we can also do by grid search CV. That is what I told. Grid search CV, rather than spending a lot of time with only logistic regression in terms of metrics, in terms of tuning, because this tuning part, metrics part, everything is common for all the algorithms. So even though we are discussing logistic regression for a longer time, whatever the concept that we discussed throughout today's session, it is commonly applicable for all the models, right? So that tuning of the model we will be discussing just after discussing the decision tree, so that at that point of time, even if you want, you can come back to the script and you can do the hyperparameter tuning with respect to all the parameters available with respect to the logistic regression too, right? So this is about defining all those metrics and playing with all those metrics, understanding all those metrics and playing with all those metrics by adjusting the threshold. Even this threshold adjusting concept is actually applicable for different algorithms. We will be seeing that in our coming session. Any doubt with respect to these metrics and threshold adjustments? Please let me know if you have any doubt. Otherwise, we can move to the next topic.
Sir, can we spend some time on discussing class weight, how this logistic regression used that?
Yeah, actually class weight we will going to address. Say the class weight only I told like it is an say some here we don't have the class imbalance problem. So if you have a class imbalance problem, then we can use that class weight so that your model will give kind of sampling will be applied internally. So it will try to make your data kind of data as a kind of balanced one, and with respect to that, it will try to produce the result. But anyway, it is not advisable to use that part. Rather than that, externally we will be doing how to bring that class balance, right? So that we are also going to do. We are going to spend some time on how to make that class balance, how to increase the weight of the class, so that I'm just giving the opportunity for my model to learn perfectly about both the classes, right? We will be doing that separately.
Okay, okay.
With some other algorithms like SMOT and other things, we are going to do it. Any doubt with respect to what we have discussed now? Shall I move to the next topic? Everyone is silent.
Maybe sir, we'll go through this, and if you have any doubt, we can ask in the next class.
Sure, always. Right, fine. So we have spent a lot of time in discussing this logistic regression and all those metrics and how to play with those thresholds so that I improve the model performance. So now we are moving into the next algorithm. So I thought of discussing decision tree as a second algorithm in this course, because decision tree is a kind of algorithm which is going to be a base model for many upcoming algorithms that we are going to discuss in this course. So the understanding the decision tree is very important in order to understand many other algorithms too, like random forest, boosting, bagging. All those algorithms will use decision tree as a fundamental block. So in the remaining time of today's session, we are going to discuss the conceptual part of decision tree. So as usual, I am taking the math part of it, but math part of it, it's not like derivative part. It is actually, I'm just taking up one problem and we will solve top to bottom. I will walk you through how to solve any given data set, so that manually we can construct the decision tree. Once you understand the process of manually constructing the decision tree, that is enough to understand all the aspects of the decision tree. Because in implementing the decision tree algorithm is same. So the way that we have implemented the logistic regression, the same way only we are going to implement the decision tree also here in sklearn. But understanding the concept behind it, it's very important. So in that context, we are going to discuss the decision tree in today's session. And in next session, the programming part in detail we will be discussing. So now, see this graph. So this is the kind of distribution between salary and age. Salary and age. And say this red class are non-defaulters. And this green class are defaulters. Right? So defaulters means the ones who are not paying the loan back or EMI. So they are defaulters. Non-defaulters are those who are paying everything properly. They are non-defaulters. So I'm just modeled this defaulters and non-defaulters class using only salary and age. Now, can you tell me, with respect to any one age, can I tell people above this age are defaulters or people below this age are non-defaulters? Is it possible to tell with respect to this data that we have in screen? Can you tell any one age threshold below which all are defaulters or above which all are defaulters? Like that, I can divide this data with respect to age precisely to understand defaulters and non-defaulters.
35. So we also have to include salary.
There is no perfect
Boundary.
But there is no perfect split that we can do with respect to age, so that I can tell who are all defaulters and who are all non-defaulters. But what is the kind of extent that I can use? What is the best possibility of the age that I can use, so that I can reasonably comment about the defaulters and non-defaulters?
35.
35.
Right, so around 35. Say around 35. Say. Right, if it is greater than 35, so I'm just going to use my age, right? Age with a condition, age greater than 35. If age is greater than 35, with respect to this diagram, can you tell if this condition is yes and if this condition is no? I'm just checking whether the age is greater than 35. Some observation may satisfy this condition, some observation may not satisfy this condition. Whenever this condition has been satisfied, when age greater than 35, can you tell me how many defaulters and how many non-defaulters are there in the group where age is greater than 35? When age is greater than 35, in that section of the data, how many are defaulters and how many are non-defaulters?
8 defaulters and 12 non-defaulters.
When greater than 35, as he told, 1, 2, 3, 4, 5, 6, 7, 8. 8 defaulters. How many non-defaulters? 12. 12 non-defaulters. Similarly, when age is less than 35, this is no. So when age is less than 35, totally how many defaulters and how many non-defaulters?
0 defaulters.
No defaulters.
0 defaulters and 1, 2, 3,
20.
20 non-defaulters. Right. So with the help of age greater than 35 condition, I can understand something. I can make some kind of decision. Suppose if I'm checking for the condition, if age is greater than 35 and that condition is not true, say that observation is less than 35, then confidently I can tell that he can't be a defaulter, right? With respect to this data. Yes or no? Yes or no? If I'm checking the age and the person age is less than 35 and the person age is less than 35, in which direction of this tree my flow will travel? It will travel in this direction, right? And in this node, everyone is actually non-defaulter. No one is defaulter. So this is actually a kind of pure node. This is actually a kind of pure node. Why I'm calling this as a pure node? Because whenever the condition is less than 35 and everyone is actually non-defaulter and no one is defaulter with respect to the data set that I'm having in my hand. So with respect to this condition of 35, I can make a decision like if this condition is not satisfied, which means if age is less than 35, I can take my decision confidently like the guy, the person whose age is less than 35 may not be a defaulter. He could be, the chance is high that he could be a non-defaulter. Whereas on the other side, if the age is greater than 35, then 8 people are actually defaulters and 12 people are not defaulters. So I can't take the decision confidently if age is greater than 35. If age is greater than 35, I can't take the decision confidently like they could be defaulter or they could be non-defaulters, because it's this node having the mixed data. Whenever this condition satisfied, I have 8 defaulters and 12 non-defaulters, so I can't take my decision confidently here. So what I need to do, I have to use the other variable. I have to use some kind of other condition once again to make some decision for this confused data. So here the data is clear, here the data is pure, here the data is not pure, right? So whenever the data is not pure, I will apply some other condition to make my decision in a proper way, in a more confident way. So here, what could be the condition I can check now?
Salary.
Here I can check the salary. So salary with respect to this distribution, what kind of range for which you can check?
20,000.
20,000. So I can keep this as a threshold. Now, say I'm just checking whether the salary is greater than 20,000. Is that I need to check this condition for this data also?
No, sir.
This 20 observation? No, right?
No.
Because here it's already pure. It has been already decided. So whenever the age is less than 35, definitely they could be a non-defaulters. If age is greater than 35, then only it is not pure. I'm not take a call about whether they are actually defaulters or non-defaulters because mixed data is there. So I'm just using some other criteria there. Age is greater than 20,000. So if age is greater than 20,000, say this condition is yes, and say the condition is no. If the condition is yes, can you tell me how many defaulters and how many non-defaulters are there? Age is greater than 35 and also salary is greater than 20,000. How many defaulters and how many non-defaulters are there?
Eight defaulters.
So age is greater than 35 means this region. In this region, salary is greater than 20,000 means this region. So in this region, all are actually non-defaulters. So how many can anyone tell the count? 12. And defaulters is 0. Once again, now it's become a pure node, right? Because there is only one classes exist under this condition. Similarly, if it is no, if this condition is not satisfied, then this is this region. This region, right, is greater than 35, but less than 20,000. The age is greater than 35, but less than 20,000 means here all are defaulters. So the count is 8 and non-defaulters is 0. Non-defaulter is 0. Further, I need to split. Whether I need to split further?
No, sir.
Because all the nodes are become pure. So now the thing is, one new data comes. Once this is a say training data. With this training data, I have created the structure. Now say one new data comes. Say one new person, age is 36 and the salary is 32,000. What is your comment about the default nature of this particular applicant? If age is 36 and salary is 32,000, with respect to your trained structure, with respect to your tree structure that you have framed with respect to your trained data, what is his class? He is a defaulter or non-defaulter?
Non-defaulter.
You are telling, so first you have to check his age. So you have to apply this data here in this tree. Age is greater than 35. Whether this condition is satisfying or not. Satisfying or not?
Yes, sir, satisfying.
Satisfying means your flow will go in this direction. For this new data, the flow will go in this direction. So it will come here. So here, with respect to that alone, we can't take a decision. So that second split we have to do. The second split is salary is greater than 20,000. So here is salary is 32,000. So obviously salary is greater than 20,000. So the flow will come like this. So this guy is a non-defaulter. This guy is a non-defaulter, right? So this I have just demonstrating with respect to only 2 variables. Now just imagine if you have 10 variables. Now just imagine you have 20 variables. So you have to construct a kind of complex tree which is having lot of intermediate nodes, lot of splits, so that once you have constructed a complete tree with respect to your train data, any new data comes, you have to apply that new data in that tree structure, and that new data is coming out of which node? If this coming out of this node, and you have to see what is the popularity class or what is the majority class in this leaf node. Here in this leaf node, the majority class is non-defaulter, right? So I'm just assigning the non-defaulter class for this observation. While I'm passing some other data, if my flow is actually taking, and it is that new data is coming out of this root node, then I will see what is the majority class in this root node. In this root node, the majority class is defaulter. So I will assign the defaulter as a class for that input data. So this is how basically decision tree works. This is how basically decision tree works. Now there is a lot of question. How can I use this age as the first one, and how can I consider this 35 as a value, and how can I use this at second level? How can I use salary, because I have 20 feature, 30 feature, right? So how can I in what order I have to use all those feature? Here this diagram is simple. So by seeing this diagram, I can see 35 is the kind of threshold that I can choose for age, but with real data, how can I choose that? Right, so like that, there are multiple questions that we are going to find the answer through our discussion. But anyway, before that, this is the basic way. This is the way any decision tree works. Any decision tree works. So with the trained data, it will just work with the split and conquer concept. It will split your data with respect to the different columns by assigning different thresholds for different columns. It will keep on split your data until all your leaf nodes are pure. Until all your leaf nodes are pure. What I mean by leaf nodes are pure? What I mean by leaf nodes are pure?
That there is no.
There will be
There is only one class 0 or class 1.
Yeah. So it is only, see, if you see, I can say that all the leaf nodes. So how many leaf nodes that I'm having in this structure? Can you tell that?
3.
Everyone agreeing that 3 leaf nodes? Leaf node are the node. After that, it is not getting split further. It is not splitted further. So how many such nodes that we are having in this?
3.
Arinath, are you saying that we are having 3, not 2? Because see, after this we are not splitting. After this also we are not splitting. After this also we are not splitting, no? Because once it's become pure, we won't split it further. We won't split it further. Suppose here there are 3 defaulters and 20 non-defaulters. I may split it further in order to bring that as a kind of pure node. But of course, that is have its own disadvantage that we are going to discuss. But anyway, is everyone understanding that this is having 3 leaf nodes?
Yes, sir.
And is there any terminology for the one level above? This is called pure node.
Yes.
What about is there any one level above the parent node?
Parent node.
No, this is say of course this is you can each and every this you can call it as a say this and this you can call it as a child node, and for this child node this is the parent, right? Again this child node is once again acting as a parent. For this is these two are actually child node. But anyway, here in decision tree we are going to use the terminologies as root node, intermediate node, and leaf node. So this is the root node. This is the root node. Yeah.
So suppose we have 4 to 5 level. So first level will be root, and the last will be our leaf node, and in between whatever we have, that will be
intermediate nodes. Intermediate nodes. So the very first node that we are using for the decision tree, we can call it as a root node. Then the very last nodes, after that there is no split, we can call that as a kind of leaf node. In between whatever the nodes are there, that we can call it as some intermediate nodes. But that intermediate nodes can be parent node and also can be child node. Here see, this is intermediate node. This intermediate node is actually a child node with respect to this root node, whereas the same intermediate node is actually a parent node with respect to these two nodes. Right? So you don't need to actually really confuse with respect to those terminologies. Just root node and leaf node is enough for us, because our focus will be on these two aspects only. which one I need to consider as the root node in each and every step, and what should be the characteristics of that final leaf node. So our focus more on that aspect. Of course, I'm just going to take to you one problem line by line, how we can construct this tree for any given data mathematically. So here I have not used a mathematical approach. Here I have just saw qualitatively, I just saw this distribution, and with respect to this threshold, I just asked you to frame the decision tree, and we done, and we have constructed some base level of decision tree. But how can I come up with 35? How can I come up with 20,000? What is the logic? For that, we need to dig math little bit more. That only. Sorry.
Sir, so what are we calling for this leaf node? Pure node? Can you spell it out?
This one?
Yeah.
Pure node. You can also call it as leaf node.
Pure P-U-R-E, is it?
Yeah, P-U-R-E.
Okay.
Because it is pure, no? So there is no overlapping of classes is happening there. So defaulter is 0. So out of 20 observations, all are belongs to non-defaulter. Here out of 12 observation, all are belongs to non-defaulter. Here out of 8 observation, all are belong to defaulter. So that is the reason why we are calling this as a pure node.
Sir, one more question. So, is there any chance that at some point of time we will not be able to decide whether it's a pure node or not?
Yeah, there may be a chance, and also even if even it is possible to create all the leaf nodes as a kind of pure node, we won't do it. We should not do it because overfitting problem will happen. Just hang on, we will be discussing all those concepts.
Okay.
Right? So we are not actually even we are not actually grow the decision tree to the level such that all the nodes will become pure. If we do like that, then it is a kind of classic overfitting model, right? So it is a kind of overtuned model. So we will be discussing that. Now, after seeing that tree construction, the ultimate question is, how can I decide that, say, I have 10 features, from which feature I have to start my split? For which feature I have to use to split my data first? Once I splitted the data with, say, one feature, what could be the next feature that I have to use to split it further? So that is the ultimate question. So that we can't do it randomly. So there is a kind of mathematical strategy how to find or how to do the split. For that, we are going to use two measures. One is Gini impurity. The another one is entropy, right? So from this entropy, we are going to calculate something as information gain. So these two are two different strategies. So you can use the Gini impurity strategy, or you can use the entropy strategy or information gain strategy to make a decision on how to identify the features on which we can do the split initially, or how to identify the feature. If you use that feature as a root node, your data will get splitted in an effective way. So how to identify those features? For that, we are going to use these two mathematics. One is Gini impurity, the another one is entropy. The formula for Gini impurity is 1 minus summation over I pi square, where I is number of classes. Now, for example, Let me give the entropy formula also. Entropy is minus summation of Pi into log base 2 of Pi. Log base 2 of Pi. So again, where I is the number of classes. Now, for example, say I have one output like this. Say malignant, benign, malignant, malignant, benign, benign. Benign.
So here, when we say number of classes, it should be always 2, right?
Always
2, 0 or 1.
Of course, with respect to that Gini impurity calculation, if it is, it should be 2. But the decision tree sklearn package has been optimized or has been modified such that even it will internally split your data and it will actually do it for multi-class also. Right, so it is not like you can use this decision tree only for binary class, but internally it will do the splitting in a binary split only. Always it will do, but it can be by doing the binary splitting again and again. It can also split the data with respect to the multiple level. But this concepts, generally speaking, it is applicable with respect to the binary class, but with respect to the sklearn package, it can have the ability to handle the multi-class also. Let me explain that so that you can understand very easily. So how it is actually, even though the binary split even though only for binary split we are going to explain this math, how it is actually do the multiple split also, that I will be explaining it. So say we are having this data, malignant, benign, malignant, malignant, benign, 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 benign. Now I want to find the impurity for this Gini impurity. Can you apply this in this formula? What is the probability of class M? This I have to explain like 1 minus Pm square minus Pb square. If I expand this formula, this is what I will get, no? 1 minus Pm square minus Pb square, right? Because there is 2 class, M and B. So what is the probability of data to be malignant, observation to be malignant?
3 by 6.
3 by
8. 3 by 8.
And what is the probability of this? 5 divided by 8.
5 by 8.
Anyone tell what is this value? And also I'm just giving one another task. For this also you just compute. For this also you just compute. So Joseph is telling this is 30. Can someone tell in terms of fraction so that we can compare?
0.4685.
0.4685. For this one?
It's actually 46875.
46875. Fine. For the second one, where both the probabilities are same. So it's going to be 4 by 8 the whole square and minus 4 by 8 the whole square. So it's going to be 0.5, right?
0.5.
And for this case, 1 minus 7 divided by 8 the whole square minus 1 divided by 8 the whole square.
0.2.
0.2.
0.21875.
0.21875. Right? So further, if you compute for one another thing, so everything is m. Everything is m. For this, how much you will get? You will get 0, right? Everyone agreeing this? For the last one, I'm getting 0.
Yes, sir.
Yeah,
Yes,
Right.
sir.
it will be
Now, just compare these Gini values with this pattern, and can you comment on the nature of Gini impurity values? What is the nature of this out of this four combination that we have written? For which one the Gini value is high? For this one, the Gini value is high, right? The Gini impurity is high, right? Yes or no?
Yeah, if it is balanced.
So what is the value? 0.5.
Yeah.
This is an
Gini
highest.
varies between.
So what is the nature of this data? And for which one we are having the minimum value? The minimum value of Gini is for this one. The Gini is 0. Compare these two patterns. What are your understanding?
Gini can vary between 0 to 0.5.
Okay, that's fine. For that is for binary class. But anyway, apart from that,
If it is balanced, then it is 0.5. If it is if
that
one
is-
class is in majority, then it will be 0.
yes. Say if the balanceness, if the homogeneity is actually increasing, your Gini impurity value is decreasing. Can you see that? What does mean by homogeneous? What is the homogeneous nature of this data? Whether the homogeneity for this is high or low?
Lowest.
Low. So this is not homogeneous because perfectly two classes are mixed in this. So this is heterogeneous. This is hetero, whereas this one is homo because all the classes are same in this. All the classes are same in this. So more the heterogeneous, Gini impurity will be more. More the homogeneous, the data is, the Gini impurity value is less. Gini impurity value is less. So that is, see the name, it's Gini impurity, right? I can say this data is not pure. This data is not pure, but this data is pure. Why I'm saying this data is pure? How I'm saying this data is pure? All are same class. Yes or no? Guys, are you getting this point?
Yes, sir.
So if all the observations are belongs to the same class, then it is a pure. I'm measuring Gini impurity. For an Gini impurity for a pure data is 0. Gini impurity for pure data is 0. If the impurities are increasing in the sense it is perfectly everything is M, but here see there is only one class belongs to B. So it is not, even though it is kind of pure, but it is not completely pure because it's having the mix of two different classes. So for that, my Gini impurity is not actually equal to 0. My Gini impurity is increasing. My Gini impurity for this is actually more than 0. If I'm increasing that impurity more, that is more levels are mixed. So here, if you see M represent 4 observations representing the M class and 4 observations representing the B class, which means it becomes more of heterogeneous. It's become more of heterogeneous. If more of hetero, then obviously the Gini value is further increasing from 0.21 to 0.5. Right? So Gini impurity is the measure through which we can understand how pure our data is. How pure our data is. Now my question is, the root node that you are going to use, how you want its impurity. The first node that you want to use in decision tree for that particular column of data, how you want to be your Gini impurity value. How you want to be your Gini impurity value?
Should be close to 0.
0.5.
0.5 or it's close to 0?
Close
See,
to 0 means we cannot
Close to
split
0.
further.
see, I'm giving one another example. Say there is one column like gender. And there is one column like qualification. And there is one output column like defaulters. Same example, defaulter or not, right? So now so the qualification is BEME like that. So now here, right? So this is say the data set. Now, even though I have demonstrated the example with respect to Guinea previously with respect to only one column of data, actually we have to relate two columns to find the overall Guinea impurity. I will take you through that. But anyway, now say by seeing this data, if I use the gender to make the decision about the defaulter or not, then can you see some kind of clear pattern, right? Whenever there is an gender is male, they are defaulter. Whenever there is whenever the gender is female, they are not defaulters. Can you see that very clearly, right? Yes or no?
Yes, yes, sir.
Yes, sir.
Right. So now while we compute the Guinea impurity for that kind of column, while we compute the Guinea impurity for each and every column, we will relate that with respect to the target. For the target alone, we won't compute the Guinea impurity. We will relate the we will compute the Guinea impurity for each and every column by relating that with the target column. I will tell that mathematical part how to do it. But anyway, say if I'm computing this Guinea impurity with respect to this gender column, I will get the Guinea impurity value as 0. Why? Because it is very discriminative with respect to my target. So gender is having two levels, male, female. Whenever gender is male, the defaulter is yes. Whenever the gender is female, the defaulter status is no. So if I compute the Guinea impurity for this gender Guinea impurity will be 0. So obviously I have to use this as a first column to make my split, because if I use the gender column as my split, I no need to even split it further, because this one column itself is clearly giving me the nature of the defaulter's target column. Yes or no? Are you getting this point? Guys?
Yes, sir. Yes.
Similarly, if you use qualification as your root node, do you think that very kind of clear relationship whenever there is a bachelor degree, or whenever there is a BE, they are defaulter, whenever there is an ME, they are not defaulter? Whether you can you see any kind of clear trend like that?
No.
No, right? So whenever there is no kind of clear trend like that, then obviously for that particular column, the Guinea value is little bit high because it is heterogeneous. Whereas here it is homogeneous, because whenever there is a male, defaulter status is yes. Whenever there is a female, the defaulter status is no. So the data is more of homogeneous with respect to gender and the defaulter target column. Whereas with respect to the qualification and defaulter column, there is a kind of mix. It is more of heterogeneous. So obviously the Guinea impurity, if you compute, the Guinea impurity value could be a little bit high. Right. So, yeah.
So in case of gender, so here you told, so impurity will be 0, right? I mean, for gender.
Yes. Impurity here in this case 0, but say I'm just changing this yes.
No, so I did not understand that part. How it is coming 0?
We will do that calculation. Just hang on.
Okay.
So the same with respect to the same formula only we are going to apply. I will give that problem, that formula step, so that if you apply in that formula, you will be getting the 0 because it's an homogeneous, right? So whenever there is a male, just if you see in terms of concept, whenever gender is male, defaulter is yes. Whenever gender is female, the defaulter is defaulter status is no. So it is perfectly homogeneous, right? Yes or no?
Yes, sir.
Yes, sir.
Right. So if it is homogeneous, say here, even though I have discussed with respect to one column, I told like whenever the data is completely homogeneous, the Gini value is 0. No, we have proved that, but we have proved with respect to one column. Now we have to relate two columns. That is the only extra thing that we need to do. But if all the elements are same, obviously we will getting the Gini impurity as 0. No, here also the same scenario, but with respect to the two column, now we are analyzing. Whenever gender is male, defaulter is yes. Whenever gender is female, the defaulter is no. It's still homogeneous by comparing these two with respect to these two columns. That is the reason the Gini value will come as 0. Anyway, mathematically I will tell how to calculate it by relating two columns. Previously I have shown with respect to only one column. We will be doing that by relating two columns. But anyway, here in this observation, in place of yes, if it is no, then how will be the Gini value for these two columns for gender and qualification?
It will be more than 0.
It will be more than 0 for both.
It will be more than 0, but still gender Gini value is less than your qualification.
Right.
Right, because still the discriminative power is more in gender.
Yeah.
So whenever there is a female, definitely it is no. But male, out of the 4 male, 3 male for the three observation, the default status is yes. For one condition, it's going no. But of course, there is some kind of randomness there, some kind of impurity is there, but still it is not too much compared to the qualification. So in this case also, I will go and pick gender as the first node, and with respect to the gender, I will split my data. Right. So like that, we have to find the Gini impurity to make the decision, like which kind of column that I'm going to use to split first. Now let me just a minute. Rather than doing that, let me straight away take you to that fine. I'll be sharing this Word file anyway with you people. You can also go through it line by line. But anyway, I have just typed line by line how for this data set the decision tree is constructed. So now in this data set we have 4 columns. The first 3 columns are talks about past trend, open interest, trading volume. Based upon these 3 parameters, we are predicting what could be the return. We are predicting what could be the return, whether you can expect the up return for your investment or down return. So past trend talks about, say, that particular share or that particular fund is actually had positive trend in past or negative trend. And also what about its open interest, whether it is the open interest is low or high, and what is the trading volume, what is the amount of business they are doing, whether it's on a high trading volume or low trading volume. So like that, these are all 3 input features based on which we are going to predict what could be the return. If you invest in that, how whether you will get that up return or down return. So that is what this data set is all about. Now I want to do the decision tree structure for this. By seeing this data, of course I have to take one root node first. Initially I have demonstrated no, I have taken the age and the age greater than 35. With respect to that, we started to split. Similarly here I have to pick any one column and I have to start to split my data with respect to that one column. So if I take the past trend, what should be my condition to split that past trend?
Positive or negative?
If I take the past trend, I am asking one query whether past trend is positive or negative. So if it is positive, how the written values are. If it is negative, how the written values are. Like that, I have to keep on do split. But I can't pick that initial column randomly. So the mathematical processes now for the past trend column, and also for the open interest column, and also for the trading volume column. For all the three columns, I want to find the Gini impurity. I need to find the Gini impurity. And I have to see the Gini impurity value. And for the which column the Gini impurity value is less, that column I will be considering as the first root node in my decision tree. Is everyone clear with this point?
Yes, sir.
So the objective is for all the input columns, I need to find the Gini impurity. Now the question is how to compute it. Of course, if you implement in sklearn, everything has been computed by itself. But anyway, here in this workflow, we are going to see how that Gini impurity has been computed for each and every column. So see here, in order to find the Gini impurity for past trend, I have to, everyone can see this, right? Or I have
Yes,
to
sir.
font.
We can see.
Yeah. So Gini impurity for past trend, in order to compute it, I have to do weighted sum of Gini when past trend is equal to positive and Gini when past trend is equal to negative. So just listen carefully. My objective is to find the Gini for past trend column. But inside that past trend, there are two levels. Or the condition that I'm going to make is whether the Gini impurity is positive, that past trend is positive or past trend is negative. So in that case, I have to individually find the Gini impurity for past trend equal to positive and Gini impurity for past trend equal to negative. So even though my main objective is to find the Gini impurity for past trend, internally I have to compute the Gini impurity when past trend is equal to positive and Gini impurity when past trend equal to negative. So once I compute these two Gini impurity, weighted sum of that is nothing but the overall Gini impurity for the past trend. This is the main formula. Now I'm just going through that first part of this Gini impurity when past trend equal to positive. Gini impurity when past trend equal to positive. So the same data I'm having here also, right? So Gini impurity when past trend equal to positive, I need to find. So I'm just going to take only the positive data. Only the positive data with respect to the past trend. So I'm just filtering with respect to only. Here I have changed something. Let me open the another file. Just for some analysis, I have changed. Let me open this PT. So I'm just taking only the positive. So with respect to this, now I want to compute the Gini. With respect to this, Gini for past trend equal to positive. So even though I have so many data, once I filtered this, I have only 1, 2, 3, 4, 5, 6 data where past trend equal to positive. For that, with respect to this return class, I need to compute the Gini. So this is very simple, straightforward as we used to compute it for that malignant and benign. So now see, when Gini past trend equal to positive, the formula is the same, 1 minus sum of pi square. Now that pi is the class probability for the observation when past trend is equal to positive. So only for this, in this Excel sheet, only for this data, you have to compute the Gini impurity. So if I compute it, there are totally 6 observations where past trend equal to positive. Out of that 6 observations, you see, out of the 6 observations, how many are up and how many are down?
4 up, 2 down.
4 are up and 2 are down. So the formula is 1 minus 4 divided by 60 whole square minus 2 divided by 60 whole square. Is everyone agreeing that?
Yes, sir.
Yes, sir.
So this is the same. The way that I have computed the impurity. The only thing is now I am just relating this with respect to the one another column. For that also I'm not doing anything with respect to this. I'm just taking only the positive level from the past trend. For that, I'm just seeing what is the return. With respect to that return value, I'm just computing the impurity the way that we have computed before. So if you see 1 minus 4 divided by 60 whole square minus 2 divided by 60 whole square, and we are getting 0.444. Right? Similarly, I can do for Guinea for the past trend equal to negative. So go to that Excel sheet and just change this filter with respect to the negative. So only 4 observations. Only 4 observations, and all are down. So what would be the Guinea? Can anyone tell?
0.
0. 1 minus 4 divided by 4 the whole square minus 0. So 1 minus 1 will become 0. So here you can see 1 minus 0 minus 4 divided by 4 the whole square is equal to 0. So now we have computed the Guinea impurity for past trend equal to positive and Guinea impurity for past trend equal to negative. Then what we have to do? Then we have to calculate for other column. No, we have not calculated the Guinea impurity.
Calculate the weighted.
We have do the weighted sum. If you see, this is the main formula in which there are 2 Guinea components. Guinea impurity for past trend equal to positive and Guinea impurity for past trend equal to negative. That we have computed now. Now I have to do the weighted sum. What is mean by weighted sum? Out of total 10 observation which is there in this data, 6 are belongs to positive and 4 are belongs to negative. So 6 divided by 10 into that positive trend, that positive past and positive Guinea impurity. So 0.444, and this Guinea impurity of past trend equal to negative. For that, the overall strength is only 4. So 4 divided by 10. Anyway, that Guinea impurity value is 0. So which is equal to 0.2666. So this 0.266 is nothing but the Guinea impurity for the past trend input column. Please let me know if you have any doubt in computing this Guinea impurity. Even though this is not really essential to do your workout in Python, you must know how these calculations are happening. Any doubt in this? Everyone clear with this?
Yes, sir.
Right? Now, similarly, can you calculate for open interest? Is it possible, right?
Yeah.
So similarly, I'm just the same thing. So I'm just now filtering with respect to open interest level. In open interest, we have levels like high, low. So we are actually calculating in the same way. And I'm just getting the overall Guinea impurity for open interest is 0.466. And also I'm just calculating for trading volume, which is the third column. For the trading volume also, I'm just getting the Guinea impurity as 0.343. So now if you see here, we are getting Guinea impurity for past trend as 0.26, open interest at 0.466, trading volume as 0.3423. Which one you will use now as a root node for your model? We have calculated the Guinea impurity for all the 3 columns, and we arrived with these 3 numbers. Now, by seeing this Guinea impurity, which column you will be take as a first root node for your model?
Which has less value?
0.26.
Which has less value. I have explained with that gender and qualification with respect to defaulter, right? So Guinea value is less means which is more pure, because Guinea impurity that we are computing is nothing but the measure of impurity. If that value is less, then it means that that particular column is pure. So past trend is pure column comparatively compared to other columns. So I'm just going to use the past trend as my first root node. So I'm just taking the past trend. So past trend is having only 2 levels, positive, negative. So rather than writing like past trend is equal to negative or past trend equal to positive, that condition I'm just checking. So yes or no. Anyway, I can also write like this as it is having only 2 levels. So if past trend is positive, there are totally 6 observations. Out of that 6 observations, with respect to the return column, 2 are up and 2 are down. Sorry, 4 are up and 2 are down. Similarly, with respect to the positive past trend as negative, there is no up, everything is down. So after doing the split with respect to the path strength, whether we are getting any pure node, whether we are getting any leaf node.
The negative side is the pure node.
Negative side is pure node. It's a leaf node. That is the reason why path strength is actually coming as a first root node, right? If you use some other root for other variable for a root node, you won't get any child node or any leaf node straight away, right? You may be in the position to split it up further to make this as a pure node. But as we are taking the path strength, we are straight away getting one leaf node. We are straight away getting one pure node just after the first split. That is the advantage of going by the logic. Here the logic that we are going by is computing the Gini and which Gini impurity, and for which column the Gini impurity is less. If you take that as a root node, the split will happen in an effective way. So you no need to do more splitting in your whole tree. Now, even though we are saying that this is a kind of pure, what about this side? Further split is needed, right? Because out of 6, 4 are up and 2 are down. I can't really make my decision very confidently at this point. So what I'm doing is I'm going for a split. I'm going for a split with respect to this part. So now, how can I decide what could be the feature or what could be the column I can use at this level to split it further? What is the column that I can use at this level to split it further?
Again, we'll calculate.
Again, you have to calculate. Again, you have to calculate the Gini values for all the columns. Or all the columns means for path strength, you no need to calculate, right? Because if you calculate path strength, you won't get anything, because only for the path strength you are getting this. So for all the remaining column, you need to calculate, and also you need to calculate only for the 6th observation, yes or no?
Yeah, subset of.
Right. So what we need to do is, so we have to take path strength equal to positive. For this section of the data, I have to calculate what is the Gini for open interest and what is the Gini for trading volume. What is the Gini for open interest and what is the Gini for trading volume I need to calculate. So that is what I have done here. I have taken only this part of the data where path strength is positive. For this is the open interest and this is the trading volume. I'm just calculating Gini in the same way. How can I calculate the Gini? When Gini, I have to calculate 2 Gini for open interest first. When open interest equal to low, what is the Gini? When open interest equal to high, what is the Gini? Then I have to do the weighted sum. That is the overall Gini for the open interest. Similarly, I have to do for trading volume. So once I done this process, I have not actually executed that part. You just calculate that. And this is the value. So Gini index for open interest is 0.33. Gini index for trading volume is 0. You can see that by seeing it, right? Compare trading volume and return. Are you agreeing that Gini for trading volume is 0?
Yes, sir. Yeah.
Why?
Because wherever
there is a high, it is up. Whenever there is a low, it is down. So obviously it's pure. It is pure. It is homogeneous. So obviously the Gini value, even if you calculate, you will get it as 0 only. 1 minus 0.5, 1 minus 0.5 minus 0.5 you will get. So obviously you will get it as 0. So what could be the next root node? What could be the next node? Next parent node? Trading volume, right?
Yes, sir.
So trading volume. So I'm just using trading volume here. Because for the 6 node only I done the Gini analysis. After doing that, I understood that trading volume could be the next node. So now trading volume have 2 levels, high, low. If it is high, if trading volume is high, I can see that all the values are up. If the trading value is low, I can see that all the values are down, right? So now all my root nodes are become pure. All my not root nodes, all my leaf nodes are become pure. So there is no point in splitting it further. So I have constructed the decision tree by using the Gini impurity concept. Understood? So even if it is having multiple columns, it's going to work in a same way. It's going to work in a same way. So by applying the Gini impurity, it's used to find by applying the Gini impurity, it used to find the which root node or which feature is suitable for root node. For each and every column, it's find the Gini impurity. For which column the Gini impurity is very less, that column has been identified as the root node. This process will be keep on continuing at the every level, so that the optimized decision tree can be constructed for the given data. Right? Now, what will be your question? While I'm with respect to this example, definitely you might have some doubt, especially with respect to the splitting and other things. What your take on how can I do this process if the data is continuous in nature?
Split it by average.
Check the variation actually.
Yes, Harinath is asking one question, like in this data set, we are actually using only 2 columns. With respect to that itself, we actually made every node as a kind of, every leaf node as a kind of pure node. So obviously, with respect to this data set, the 3rd column is insignificant. That is the reason why this tree-based structure can handle the feature importance by its own, by doing the feature engineering by its own. Right, so it will actually pick only the appropriate feature in this process. So that is one added advantage of this tree family. It won't use all the insignificant feature for its model building. Right, so now the next question is how this will be get applied for the numerical data. How this will get applied for the numerical data. Say for numerical data, what it will happen is, quickly I will discuss that and we will finish this finish today's session. Say now trading volume, I'm having some kind of continuous number. So if I want to find the Gini impurity for trading volume, what you need to do first is you have to arrange this data in an ascending or descending way, right? So you have to sort this. Right, so trading volume I have sorted like from lowest value to highest value. So 280, 300, 320, 340, so on up to 760. So now they will calculate the moving average. So moving average means just take the average of these 2 numbers and tell what is the value. 290, right? Yes or no? 280 plus 300 divided by 2.
330.
330. Yeah.
No, 290. I mean the.
Oh, okay. So here 300, 320. So next moving average. These 2 number average is this one. Then 200 to 320 averages 310. Right. Then 320, 340 averages 330. Right. So then 340, 360 averages 350. Then 360, 575 average. So like that, I'm just writing x1, x2 some number, x3, x4, x5. Right. So now what it will do is, so we have your model will consider all those numbers as a thresholds. First, it will compute Gini impurity with respect to the condition. With respect to this condition, trading volume is greater than 290. Whether the trading volume is greater than 290 or not. So it will just filter your data like it will compute the Gini impurity with respect to this level 290. Previously, we have computed past and equal to positive. What is the Gini impurity? Past and equal to negative. What is the Gini impurity? No, like that. Now it will compute the Gini impurity like trading volume greater than 290. What is the Gini? Trading volume less than 290. What is the Gini? And what is the weighted sum of that? So with respect to the trading volume 290, it will compute the Gini. With respect to the trading volume to 310, it will compute the Gini. With respect to the trading volume 330, it will compute the Gini. So on, it will compute for all the combination. Out of all the combination, it is computing. Say if the trading volume with a condition 330, that is trading volume greater than 330, less than 330. For that, if your Guinea impurity is less, say for this Guinea impurity is less, then it will split your data with respect to the trading volume 330. Got the point? As here there is a level, we are just computing the past trend equal to positive, what is the Guinea, past trend equal to negative, what is the Guinea, and we are computing the overall Guinea. Now, with respect to all those numbers, it is actually computing the Guinea. With respect to data greater than 290, less than 290, find 2 Guinea and find the weighted sum. So for this, it can find one G1. For this, it will find one Guinea G2. For this, it will find one Guinea G3. Like that, for all the possible threshold, for all those moving average, it find the Guinea, and out of all those Guinea, it will see which Guinea value is less. That particular level it will use for this trading value to split. Got the point, everyone?
Sir, what about the percentile method? Like we divide data in the 10 equal part and
say you are talking about developing your own algorithm, right? So like say here in this ID package or in this C4 package and all those things, for a numerical column of data. So this is how the process that I have told. This is the way that it is actually computing the Guinea. Of course, here there is no way that it will miss out any kind of scenario, right? Because it is taking the moving average. So for each and every number, it is like even if you are doing some kind of calculation with respect to the sales data, the sales data minimum value is say $5 and maximum value is $100 or $200. For all those number combination, it actually used to find the Guinea, and for which number, if it splits, that homogeneity will be more. So that it is actually calculating, and with respect to that, it is doing that splitting.
yeah. So in cart actually using this algo or what? This
This one only in sklearn decision tree. This logic only it's getting used
in cart. Okay.
Yeah.
For the continuous this variable, that part I did not get. So if you can cover maybe in next class, I mean in detail.
Yeah, of course, I will once again refresh this in next class. But anyway, this is only that explanation, or we can't even manually calculate because this is a kind of uphill task to calculate it. And also in package, it will happen internally. But anyway, I will construct some kind of decision tree with the diagram and other things. Let me show you how it is actually threshold values in decision tree. But anyway, once again in our next class, before going into the coding part and other thing, I will be just briefing you once again how this Guinea impurity is getting calculated for this continuous number. If you maybe you people now reached that threshold level, so we will be discussing once again this part in the next class.
Yes, sir. Very well.
Sir, how this will work if I have more than 2 levels?
Exactly, good question. So if it is having more than 2 levels, still it will actually say there is some chi-square based decision tree that people using, in which even it will split into 3 kind of levels. Like say if past trend, you have 3 levels like positive, negative, neutral. Even though if it is having positive, negative and neutral, it won't split into 3. Right, always one parent node in decision tree with respect to sklearn will have only 2 child node, even though if it is having 3 level. Then how it is handling that situation in the sense, it will ask the question like past trend is equal to positive or not. If it is positive or not, for that you have to compute one side is for positive or not, the another side is for both negative and neutral. Are you getting my point?
Yeah.
So like sir, one versus all, right?
Sorry?
One versus all. Like if you have 3 levels,
yes,
one level,
exactly.
and then 2 is the other level.
Yes, because once it made this binary split, then at the second level, on the second level under one branch, only the negative and neutral is there. No, that time on top of it, it once again may check like past trend is equal to negative or not. Right, because now it is having only 2 levels there, negative and neutral. So like that, even though it is having a multiple level, it will do in a binary way only. So always the split is binary. Always it will split this or that only. Whether it's a continuous or whether even a categorical column is having more than 2 level, it will go by a binary split only.
I
Got
think
the point? Yeah.
otherwise information gain, I think multiple split is right.
No, even for with respect to the information gain, here in sklearn package, always it's only 2 split. Information gain calculation I have given. Anyway, next class I will start with that information gain concept. That calculation in this same document I have given, how to calculate the information gain. So the calculation almost remains same, and also it's a log 2 based calculation. Don't try with your log 10 or ln. This numbers that I have projected with respect to the log 2, I have used the online calculator to arrive with this number. So here the same concept. The only thing is, after computing the information gain, we have to choose the node or choose the feature which is having the highest information gain as the root node, right? So anyway, that information gain entropy part we will be discussing in our next session. I don't want to just hurry up that thing at the last minute. But anyway, the concept remains same, whether you are using Gini or entropy. That math part will slightly differ, but that the way it is actually splitting all those things, all the other things are remain same.
Sir, maybe if you can share the same, same document for the continuous variable, any one example, that would be.
Yeah, that's why I told no, I can say, just imagine I have to calculate this many. So it is, I have to calculate this G1, G2, G3, G4, G5, G6, right? So let me just do it for any one, say for this 290 or 310 alone, I will calculate and I will send.
Yeah, sure, sir. Yeah.
Right, because of calculating for all those moving average is a uphill task. Right, I will calculate for this 290, say with respect to this data for this 290 and 310, I will calculate and I will send it to you. Similarly, you have to calculate for all the things, and you will get a lot of Gini impurity. Out of that, which Gini impurity is less, that you have to take in as the level to split that particular column. Fine. Any other doubt? Any queries?
No, sir.
Fine, guys. If there's no more queries, I'll be sharing those things. So you just go through it. This Word document also. So next class, we will be continuing with this decision tree programming part, followed by hyperparameter tuning and all those stuffs. Right? Thank you.
Sure, sir. Thank you.
Thank you, sir.
Yeah, thank you, sir.
Thank you,
Thank you,
sir.
sir.
Thank you all.